I feel like I should have let my beard grow.
Sorry, I didn't understand, Mark.
I feel like I should have let my beard grow. I'm looking at a bunch of
yeah.
It's like Lord of the Rings here. I feel like I should have
Oh, you're right. He looks like Gandalf. Sorry, I didn't understand, Mark.
I feel like I should have let my beard grow. I'm looking at a bunch of It's like Lord of the Rings here. I feel like I should have
you're right. He looks like Gandalf.
You know, the jokes get funnier when I hear them the second time. I feel like I should have let my
Somebody has an echo. I think somebody's watching it on YouTube at the same time.
You know, the jokes get funnier when I hear them. There we go.
It was El Pocho.
Sorry guys, sorry. There's some echo there, so I will ask people to put microphones or to sorry, not microphones, to put headphones or to mute yourselves.
We actually think that you were the echo because it went away as soon as you put your headphone on.
That's right.
It was mine?
We think so.
Are you watching the YouTube live streaming at the same time?
Oh, because I have that. Yeah.
That was the issue. Yeah.
Okay. So yeah, but now, okay, it's something. Yeah, it got open at the same time, and I'm not sure which audio it's working, because if I mute YouTube, I stop hearing everyone. Well, okay, so I think that we are more or less ready, right?
What you could do is you could open YouTube on a tablet or some other device, and then put that one on mute.
Yeah, I think maybe I will leave it as it is right now. I think right now is working. So
yeah, it's fine. Yeah, but you don't need to leave it open for the live streaming to work. Just to let you know, if you want to see the chat, that's why you need to leave it open. But if you don't want to see the chat, it's not necessary to.
Okay.
Leave it open.
Okay, I was having a lot of trouble because it has some delay. So I closed now. So could somebody speak right now?
Hola.
Okay, so it's working. Okay, I think we are set up. So just let's start, right? I don't know if everybody's here. Well, I think we are missing Eliot yet, right? But it's time. So maybe he will join later. Okay, I will just start. So first of all, I want to thank FAST Foundation for being the foundation that supported us to do all this. Thank personally to Leandro, Gabriel, Inés, Maxi, that helped me a lot with all these things that needed to be done. Also to thank Labware that made a donation so that we have this Zoom account, and of course to the audience and to the speakers. And well, so the first thing that we are going to do is a four-way panel that was recording the past week with Eliot, Boris, Jan, and myself, and that expresses more or less the ideas that we were thinking and that led us to make this hackathon. So as it said, without further ado, I will just start that video. I'm going to share the screen. Can you see my screen?
Yes, we can.
Perfect. Then just let's start.
No sound.
No sound?
No.
No.
Oh, this is weird. I had to. Okay, I will close it and start it again. I have to do something with
By the way, the
Zoom about
screen that we see is the gallery view.
Yeah, it's a gallery of 4 people, right?
That's correct.
Yes.
Okay, that's fine. So again, I'm going to share it again, but with optimization for this and this. So,
well, welcome everybody
Do you hear
to this VM Hackathon.
Yes.
Good.
This is a very exciting development. Boris and Jan contacted me a few months ago to investigate collaborating, not so much around COG as the notion of meta VMs in Smalltalk. Meta VMs being virtual machines for dynamic languages, which are implemented in dynamic languages. They may go through various translations until they arrive at the metal. But what we have found, and there are several groups in the world which have found this, is that developing virtual machines in dynamic languages gives one incredible productivity compared to using more static approaches. And we're all excited and energized by this. And on the one side, we see the advantages of using dynamic languages to implement dynamic languages. And on the other side, we see a rich computational universe, which is much bigger than us, which offers us things that we want. And so Boris and Jan and Pocho and Richie and myself, being energized by this, starting to investigate how we can pull ourselves together, enrich each other, support each other, follow this vision of meta VMs, and at the same time not be the traditional isolated small talkers who are not benefiting from what the rest of the world has to offer and reinventing the wheel endlessly. So what we thought we'd do is to start by discussing those ideas and filling in the details. So here we are, the 4 of us, wanting to welcome you and wanting to have a panel discussion outlining those ideas.
Yeah, I couldn't agree with you more, Eliot. And well, I think that everybody here has a huge love for Smalltalk and a wish to do things with Smalltalk in different ways. Each of us has different projects, have been working on different areas, and yet we are here together. And this has to do with the title of this panel, which is that you get faster if you are alone, but you get farther away if you are together. So I think that one of the main goals of this reunion is to align ourselves as a community so that we can do with the Smalltalk we love whatever we want in a way that is sustainable and that can reach further.
Right. As Pocho, I can't agree more with what you said, and Well, yeah. What I wanted to say is that, we're doing a lot of things, but we cannot do everything. So it's important to see what the others are doing and other people are doing great stuff too. It's not only us. And there is a lot of research and a lot of tools that are out there, being simulators or tools for validating software, whatever that means. Whether proving or some sort of fuzzers or whatever it helps. We should probably reach out and look what's there, and also work with the other communities together to to improve these tools such that they suit us but also suit the others. So if you work on Smalltalk, it doesn't really mean that you work only in Smalltalk. If there is something in some tool you want to use, but just some functionality missing, then why not just fixing it? And that's the way to go. And then it means that we are playing much bigger game than just doing, quote unquote, just doing a Smalltalk VM is not an easy task. But the world is much bigger than a Smalltalk as such. So that this is something I see as important, and having all these tools available give us possibility to be even more productive. That's my experience for past some time.
Well, I am really glad that we are all on the same page. This is the goal of this hackathon more than to achieve any particular progress with whatever any private us are trying to do, even though we think we do have very interesting ideas, each of us. The idea is much more about how do we achieve alliance and a common direction, and how to have a common upstream in the fundamental technology that we are developing, other than any of the particular Smalltalk VMs. Because the tragic situation of disconnect that has been going on for years and years is not because we're trying to fight each other, or not because we are hostile or evil to each other. The problem is distance between the different boats in the ocean. So if the ocean is huge and we are a very, very tiny community, very, very tiny number of people, then you don't even see each other from one boat to the other. All you see is just ocean, and there is no overlap. There's no connection, simply because the space of possible designs and the space of ideas of what you can do and what you want to do is so huge that this, what Jan just said, becomes very important. That you cannot really do the whole idea of if you want to go in a particular direction, you cannot have it all yourself. There are pieces of computer science that you need for building any of the Smalltalk VMs that we want, that hundreds of people, of very, very smart people, have worked on and got their degrees and have been working for that for collective hundreds of computer scientist years. And the result is that they are very much ahead of us. There's a lot of very interesting technology out there that they're winning over us in attracting people just simply because they have advanced really, really interesting ideas too. And if we say that attracting people by just negating what others are doing, and we are the only people who have interesting ideas, is just it's bound to lose automatically. We have to be open to collaborate with these other communities. There's a lot of new computer science that has already proven itself, and everybody is using it, and our competitors are playing in that space very successfully. Be it GDB, Gem5, OMR, various new theory improving tools like Microsoft Z3 and Coq and New Perl and all of them. We cannot simply ignore all of these things going on. So there's just two principles that I see for this hackathon. One is bridging the gap between the different approaches to the Smalltalk VM by unifying the upstream technology. And that means the sessions where we will do the unified JIT APIs for PowerLang, B, Cog. That's one, and the other topic is bridging with technologies external to Smalltalk. We're going to see how to use processor description technology. We're going to see how to use debugging technology, how to use theory improving technology to automate the construction of VMs, and each one of us has some, how shall we say that? Some connection to the outside world, right? Because like Jan with GDB and like we have to formulate that somehow more nicely. That yeah.
So just for those, because I wasn't aware of it, OMR is the open managed runtime. It's the kind of what Java, meta Java is, right?
I would be careful in saying Java in particular, because that has nothing to do with Sun/Oracle.
Right.
That's IBM's, and I wouldn't associate it with Java, because that came out of the Smalltalk world, right? This was the OTI Smalltalk machine, and then it became the universal machine where we had Smalltalk, and then we had a Java execution mode, and it's just that now because of the business that IBM is doing for the business application of that machine is mainly Java. That's the only reason why there is people are associated it with Java so strongly. But it's the OTI universal VM. That's what it is.
Right.
Yeah, that the OMR tries to be, kind of a distillation of what do you need to build a dynamic language runtime. And it's kind of, they try to be sort of like a Lego approach. So you pick what you want, and what you don't want, you just leave out. Obviously, this has been developed inside IBM for years. And it's a huge
decades,
pile
I
of
would
C++.
say decades, since the 90s.
Decades.
Yeah.
Yeah. And it's a pile of C++ code. But what is, from my point of view, very interesting on it, and why it, from my point of view, makes much sense to at least follow, is that they are really trying to modularize the thing.
Mm-hmm.
And to draw the boundary between the JIT compiler and the garbage collector, for example. And these are difficult things, because everywhere
I think that there is, I think yes, there is the boundary between the JIT and the GC. But I think there is an even more interesting example of that, because the boundary between the JIT and GC is in the middle of OMR. But there is the boundary that goes between OMR and J9, which is like for Eliot's benefit, I will say that I will use parallel to how things are done in COG. In COG, you have the abstract compiler, and so you have n+1 instances of that, right? So if you have n RTLs, you have the n RTLs and another instance that is called the backend. And it's a special thing which is not, the COG abstract instructions, these n instances, they are like the trill instructions that are in OMR. But the backend is what in J9 is in the actual Open J9 even project, right? Not even part of OMR, because the backend does things like, well, how do you patch addresses inside the jumps in the PIC? In J9, the distinction is very interesting. Is in that that has been understood like more than 20 years ago, that there is a very large distance between emitting the JIT code and which can be expressed in not language dependent way. So in OMR we say, well, this is for any, can be for small, for something, but how you patch a PIC, that is very language dependent thing. So in that sense, there are very they are very loud in explicitly saying that these two functionality are completely different parts of the universe, where in COG, they're actually in the same class.
So without diving down too much right now, because it's something that we can address later on, to continue our introductory conversation here, we have some meta goals. Jan articulated as we were discussing before this meeting how important it is for our community to get new blood. And Pocho, you had talked about at least two groups of audiences that you thought that the entire hackathon was addressing in terms of people watching, not necessarily the participants. So would you tell us a bit about what you thought those communities are?
Yeah, okay. So I think that we have, of course, we are doing a VM hackathon, so there's going to be an audience that is fond of working with VMs. And of course, those are going to be the ones who get most of these talks, I guess. But I am also interested in broadening our audience so that we can let all small talkers that are interested in understanding and in improving VMs to get something from these talks and from this hackathon. Because of my particular view, which is that that VMs, well, VMs are hard to call and hard to create, but they should be easier to understand, and it should be easier to improve them. What I see in most VMs I've seen is that they are extremely powerful, but yet that comes with a level of complexity that is huge. So you have to be an expert to change anything on a VM. What I would like, this is my personal view, and what I would like in the future is that people who are small talkers or people who are application level programmers can write improvements to VMs and can understand how the VM works so that they can understand what will work and what won't work with their code, even on application level. And I would like those people to participate here in the hackathon so that they will learn how to write code for these different VMs we are going to work on, and to understand what they are made of, and any particular piece that they are interested in, that we can show it and they can get a good idea by looking at the code. That's what I would like from this hackathon.
So how are we going to wrap up this this panel? You know, we've kind of set the stage. We've set our meta goals. I suppose you know, I want to express. I don't suppose I do want to express my excitement at the next few days of meeting people and talking and working together. And I want to express my greater excitement at the beautiful forging of a community, something that, you know, I've been lucky to be involved in the Smalltalk community since 1983, and I've had some superbly enjoyable times being supported by the Quack people in starting COG, in working with Clement, and in working with lots of other lovely people doing COG. But this is kind of the first time where I feel like I'm not setting direction here. There's some people here who are extremely powerful and have an extremely clear vision and rationale for looking at other technologies, other approaches, and that we are able to cohere, to relate to support each other, and it's kind of really momentous time for me. The thought that I will be working with people with much better ideas than I. You know, the great. I can't remember who said it. But I think it's somebody from Park. You know, you never want to be the smartest person in the room, right? And it's so important. You know, you benefit from other people, and you know, I have that feeling with Clement, and I have that feeling with Dan, and I have that feeling with everybody here, and I'm very excited, and I hope that. No, I'm sure that the next few months and the next few years are going to be incredibly exciting and enriching. So I just want to say thank you.
Well, also thank you, Eliot, for those words. I am really glad that you are here today and that you are excited about all this. This is, I think, this is good for the Smalltalk community, not only us, but also for the community, to present alternatives, try to make our projects something that can be used by other people, and at the same time to have fun, because one of the things I like about these things is that I have fun every day. So this is something I would like to continue doing for a long time. Okay. So screen sharing is closed. Okay, so how shall we continue? I think we can do a little small discussion here, not very long, because we have to do more stuff. But so, for example, I would ask Boris, Jan, Eliot, what should we get then from this hackathon?
Yeah, it's great. It's a great question. I think what we should get is a lay of the land and the directions that we want to go in, and where are the things that we're working on right now, and where are the things that are slightly further off. And I think we should get try and get a really strong understanding of things like the B metacircular architecture, and maybe the central cog JIT stack simulation architecture, and how those things can synergize, and the work Boris is doing on automating the generation of the back end. But that's only that's the JIT. There's also stuff to do with garbage collection and interoperability, and so that's on the one side. And then on the other side, we're inviting people who are interested. I'm astounded by the audience here. There's 25 people here, which is fabulous. I want very much to hear what directions people think that we ought to be moving in that we're not.
Yeah, and also for me, what I would like, my personal quest for this hackathon is to let people not only understand how the metacircular VM works, but to let people see that making VMs can be easy. Maybe easy is a relative word, but yes, we can make VMs that are not that hard to understand, and that should be the way what I think should be the way VMs should be constructed. Boris, do you have some words? Of course he does, I guess.
I do, and I will be taxing your attention for the next 25 minutes anyway, so...
Okay. So, well, I don't know if if Jan or someone from the audience wants to add something else, or we shall continue to the next topic, which is Boris talk.
If I might, I would like to ask a question. Are we open for questions?
Yeah, of course.
Well, now comes the second question. The four of you have been talking about two things, I guess, or at least I see. One is an expectation on telling others the kind of stuff you are doing and getting people involved in building VMs, and maybe something different is the stated objective of converging efforts. Is your intention to discover how to do that during this hackathon, or do you already have a plan?
Well, we have a vision, right? We have an idea of how we can make different VMs converge. So we haven't done that yet, but we plan to explore on that during the hackathon.
Okay.
And I think that it will work, and that will give us a lot of things to do after the hackathon. So, but yes.
Okay, thanks.
One of the things, I don't know whether we addressed it in the opening panel, I can't remember now, but we did talk about it over the weekend. One of the really important things, both for the B work and for the COG work, is that at all times we've avoided the Park Place mistake. We've kept the VM in production, and we've moved it forward where we can, even if we haven't moved it forward at the kind of pace that we want. And what we haven't done is kind of stop in dissatisfaction at where we are and pause while we do the kind of research reach for a really interesting place. So we've been pink playing all the time, and personally, I don't see that as a disadvantage. I think with the resources that we have to remain pink playing. So that it's really important to have a great vision, but it's equally important to remain in use as you go. So in charting the mix, we have the challenge of keeping the VMs functional and moving forward in a sensible direction. So there's kind of the need to have the experiments being quite close in a kind of an agile way. That's reminds me of the kind of approach that Lam Research has to silicon development, in that they look, when they're working with PhD students, to look at latest surface physics that they use in their processes, they look to have 3-month cycles with their PhD students so that they can change direction as the science evolves. And I think that's a good pattern for us, that we're going in a very interesting direction. That metacircular VM is probably the most elegant and the most complete metacircular VM, and certainly that I know of. And in moving towards that, just don't want to make a misstep, and I don't want to stop moving towards it. It's really important that Javier is about to release the VM that Gilad and Richie and Javier and I can still remember us talking in FAST 2010, and it's really important that work is still existing and still about to be released, because in most other efforts that are at all similar like it would have died, and so yeah, we're very much that kind of the overriding meta goal that we didn't even state, which is implicit in the new blood goal, is staying alive, and so trying to go in that relevant direction while still breathing is really important.
So if I could, as a sort of distant observer of the Smalltalk VM scene at this point, add support to what Pocho said. I mean, from my perspective, you're competing against these monsters and the odds are very much against you. And you need to leverage something relatively unique as an advantage. And sure, part of this is you get a bigger group of people and you don't have more Smalltalk VMs than Smalltalk users, someone sometimes feels. And that's an exaggeration, but unfortunately not by enough orders of magnitude. And so that might buy you something, but that will not make you competitive with mainstream VMs, because every team that's working that is more than all of you put together already. If you want to get an advantage, you need like Smalltalk, you need a fundamental advantage. You're working with a much more productive technology that'll give you a multiplier. So I just wanted to add that for what it's worth.
I agree with that, Gilad. It's one of the things we were talking about during the past week, that the productivity improvement that we see in working with this kind of meta VM technology is one of the key factors that has left us to still be on the run, because we are very small teams, but yet we still get to continue working on VMs. Okay, I guess that we are ready now. So Boris, it's your time.
Yep, let me share my screen. Hi, I am very grateful that I am able to speak to this distinguished audience today. I'll begin today's talk by jumping right into the middle of one very narrow example of the general debugging approach I want to present. Even though I am quite conscious of the criticism why I never start from explaining the wider canvas. But I think this way of explaining is consistent with my vision of Smalltalk 25 and Diophantus Arithmetica as the ultimate Dynabook. This summer, I was trying to put Eliot's Open Smalltalk onto my symbolic engine so you can benefit from his decades of effort in the VM logic and at the same time do things like put variables into holes and propagate these variables to emitted machine code and further into its symbolic execution opens the door to all kinds of interesting things. And the key to that is getting rid of the dichotomy between the simulated and the production VM. The first step was to replace the alien with an interface allowing the VM simulator to run interchangeably and seamlessly on anything from real stock silicon to symbolic processors. After that was done, the next step was putting in a more interesting RTL concretizer. But I didn't want it to be academic. I wanted to size how deep was the rabbit hole between a toy prototype to a real VM. And with Open Smalltalk, this situation is kind of tricky because that ramp is not continuous. The reader image looks deceptively simple. You'd think you are just doing 3 plus 4, but even booting to the prompt, you need the whole startup sequence, all the blocks, processes, process switching, and you need the whole VM. So a convincing experiment was to get the system to boot to the prompt on a processor not supported by the COG JIT compiler. I did it on PowerPC because it's fully open source. That new community is a huge deal. And on a sheer personal level, I've been loving that processor since 1994. So I had to implement all the pieces, and it looked like I had everything working wonderfully, but there was this last bug where after what appeared like correct execution of thousands of instructions, it would go into a strange infinite loop. And I couldn't figure out why, because the branching decision was made at a level much higher than the assembly I was looking at. So let me walk you through my actual working process, how I fixed this last bug. The first thing we need is a running target with a GDB server to connect to. I'm going to use the thin shell. What it is just an empty ELF file with a bunch of zeros in the process image. And to run it, I'll use Gem5, but this system can use any GDB server. Okay, now that this is listening, see here, now I can start my COG VM simulator connecting to that RSP server. And it takes a bunch of time, and you will see that this just never finishes. So something isn't right, something is looping. Well, it's very difficult to see what they are just from the assembly that's going on here because of the very large distance in abstraction. Let's try. So let me stop this and grab some random address and try to see what's going on. I don't know, something like 25C14, like for example here. It's a good one. It doesn't matter which. Kill this. And then let's close this. And the The tool gives you many good ways to insert hardware breakpoints. I just do something simple. And now if I start this again and go here and run this, the breakpoint is gonna cause a hardware trap. This is starting. And you see, it immediately stops, and this is because we are in ULD. What is this? There are three sides to looking at a target. There's the target process itself, and some agent gives you control, say through an RSP server port. You need something to sit on the client side of that RSP wire, and we now have a Smalltalk implementation. And you need to be somehow able to interpret those raw bits as a Smalltalk VM. So switching between debugger panels means you've got your usual Smalltalk debugger, ULD, and VDB. Although as of today, ULD and VDB are not integrated, and we'll try to do something about that at this hackathon. But when I was debugging this, I had to satisfy myself with a much more primitive VDB stand-in. So this is the ULD perspective. On the right, you have the status of the target CPU. All these tools, they're not written by hand, they're synthesized from the processor specification. Let's see what was going on with the assembly here. So first, there was lis into register 12, and now as expected it contains 0 here. And now we're just about to add the short immediate -12 into that register. So I can simply do a step 1 instruction here, step I, like in GDB, and now you see that my R12 contains -12, and then I add the contents of these registers to my register 11. So this is the stack here in R11 and R13. They pointed the stack just like on ARM. So basically we're popping here. If I step I again, my R11 just got decremented. And then I am loading into register 7. Now on the left here is the post-mortem stack of the nativizer or of the JIT that produced these native instructions. Basically explains what was the JIT thinking when it was emitting all of that assembly. So we see that it's in pop to reg, and reg here is R7. So these 4 PowerPC instructions here is what makes up the move MWRR RTL. And if we walk down the stack, we can see the workings of the JIT, and that it was trying to compile a cog method, and we could investigate what the selector was and so on and so on, but that still seems too low level. Let's look at it from the third perspective. As I said, this is very, very primitive, and we're gonna replace it with Jan's VDB. But at least we can see something. We can see that it was going here, just beginning to start up the image, and then it sends start up to all the classes on the list. And we are initializing the class small integer. And even though we don't have nice things, syntax highlighting and variable names, and we don't see where the PC actually are, we are kind of beginning to understand what is going on here. This is trying to deduce the width of a small integer without explicitly asking the VM. So this val right here is temp2, and we're doubling it into next, which is temp1. So we see that this has already happened, and we keep doing it until it overflows. Now, if I hit proceed in this perspective, what's going to happen, we're going to send the continue packet to the GDB server, and it's going to keep running. Watch this. So we ran until we hit the same breakpoint again. And now, if I go into this debugger here again, these temp1 and temp2 variables are now twice as big. Let's see how many times do I need to repeat this before I see something interesting. Okay, 10 times. How big is the value now? Okay, another 3 clicks. 1, 2, 3. Go to DB again. So it did overflow, but not into a large integer, but to the small integer 0. See, the previous one here was 8000001, which is the most significant bit. So when you shift it left, it overflows. And then if I proceed, val is now 0, and val plus val is 0, and next is 0, and now this is going to continue forever. Can I spot why? If I just scroll here, right away there is something suspicious right in here. This d equals 4 blah 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 looks exactly what we're after. So what if we break at 2605C? Well, it's too late right now because we already looped into 00000 pattern. Just kill and do this again, but 2605C. That. There. So I'm adding register 5 to register 22, and the result stays in 22. So 22 is my minus 32K sign extended. And 5 is the same with integer tag. And now I step 1 instruction, and I'm in the next tile, but I can look at my R22. It got 1 bit to the left, and I have my small integer tag. Now let's continue, 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 continue. Where am I? 22, I'm there. Am I there yet? FC. I still have a bunch of bits left. Now I am F. And now I am E, which is 3-bit set, and R5 is at E. So again, 3-bit set, and one more is C, and then one more is, see, there is 8, and R5, also 8. Now it should overflow when I add them, and it should be 0, 0, 0, 0, 0, 1, and then the overflow flag should be set. So we just step in one instruction, and now I am you see the next tile is jump if overflow. On PowerPC you have these short flags, so to get to the overflow bit you need to move part of the exception register to whatever particular condition register you're interested in, and then there is this branch conditional. Well, let's look at the flags, and you see the overflow bit is not set. Okay, now I understand that the problem is not with the JIT. The problem is with the implementation of the add instruction itself. This should have been O dot instead of just dot. But the problem was that this particular combination of OE and RC flags was causing Gem5 to crash. But I just wanted to see how deep the rabbit hole was in terms of getting Open Smalltalk to work. So I short-circuited the bug in Gem5's implementation of PowerPC. And now it turns out that there's no way around actually fixing the bug and contributing the fix to the Gem5 community. So let's stop this again. And for the sake of time, I'm not gonna show you how I fixed the Gem5 bug. I'll simply get the new version and then recompile. And when this is done, we'll restart and restart this. And I'm no longer interested in this breakpoint to show you. I'm gonna fast forward a little bit in the pre-recorded talk. To show you that indeed we are reaching the REPL prompt after 0.3 seconds of simulated time. Now, frankly, none of this is in itself that interesting. What is interesting is the meta question of attitude. The debugging of this bug has reminded me a couple of years ago I was watching this funny YouTube video. I think it was called Debugging Under Crisis or something like that. In the video there is this major cloud provider. They practice this Google-like Fridays are spent on whatever interests you practice. But at the same time, their management thinks that because this is a production company, debugging falls within those personal 20%. And then there is this catastrophic outage bringing down their whole cloud. And they're like, how can you be staring at a debugger screen when the company is bleeding money every second? So obviously this is extreme, but when you turn it around 180 degrees, you start thinking of Alan Kay's reference to Kahneman's fast and slow thinking. You have reactive mode of the brain. So a bug report comes in, you try to, as quickly as possible, find a change that will make the bug go away. You push the patch and you are ready to service the next ticket. As opposed to the cognitive mode. I'm just trying to understand, to discover the truth, to get insight. And when this is done systematically, this is called science. And here is the most important question about the fundamental design of my debugging tools. Is it an instrument for reactive activity or an instrument for cognitive activity? And according to what systematic principles do I engineer these instruments to enable my brain to stay in the correct mode? Thank you.
Boris, how do you do the tie-up? How do you engineer the tie-up of generated code with the JIT state that produced it?
I add a map. I will show you in the code in the hackathon that there is a map every time you do one of those gen, right? So there is I don't know, move AWRR we're looking at, right? So the move AWRR with the capital, that goes into gen move something, and that goes into gen instruction. And the very last line of what I do in gen instruction is, this is right, so it generates the RTL, and then it concretizes the RTL. The concretize goes into dispatch, or the other way around, doesn't matter. And right after you have concretized the RTL, I look at what the address is I just touched, and I look at this context, and I have a dictionary, and from each address that I just touched, I map them in the dictionary to this context that I just captured.
So you copy the stack every time you do a gen.
Yes.
Right, lovely. And so that's an option that you switch on because you don't do that all the time.
Yeah.
Right. Yeah, that's really brilliant because that's a huge improvement. Because up until now, I've taken the repeat where you find the bug in the machine code, you note the address, and then you back up to the generation, so you find out the index of the instruction, and then you back up until you get, and so just capturing.
Yeah. And I was doing this this whole summer, and I grew tired of it, and I wrote this debugger panel that just I can just step through things But not just step through things. At each processor instruction that I am executing on the processor, because remember, this is not the alien simulator. This is, you know, any target you want. Instead of every time trying to investigate, well, what is this? What part of what RTL this is? Because also remember that I am new to COG and I didn't understand what was going on. I wanted to have a tool to allow me to understand very quickly what the JIT is doing. So yeah, that was the motivation to write this.
Yeah, I shall be stealing that next week.
So do we have other questions? You can, I don't know if you can unmute or raise your hand or write questions in the chat. While we wait. So one thing I was surprised, Boris, was that you could do that. What you are actually doing is like traveling in time at two different times at the same time, because I don't know whether you paid attention, the ones that were watching the video, but on the left hand you had what the JIT compiler was doing, and on the right side you had what the machine was actually executing, or well, the Gen 5 virtual machine was executing. So what the JIT was thinking was something that happened a long time ago, right? And that's the kind of questions that you always ask when you start looking at assembly. When you get to the point that you are debugging assembly, is like, okay, what was the JIT compiler doing when it generated this code? But because this code is crashing. And I was really surprised that you could save all the frames or all the context of the JIT compiler while it executed, so that then you could go back in time when the Gen 5 was executing and see what it was doing, because you have everything or almost everything. You have the variables. It's not that you can only see the frames. You can see the frames and the contents of those frames, everything. It's amazing. Okay, I don't see any raised hand, any question in the chat. So I guess that we should move to the next. I don't know if Gilad was making some kind of something now. Okay, so let's move on to the next talk. Jan, are you ready?
Yes, I hope so. I won't be more ready. So let's start. Okay, let me take the screen. You need to allow me.
No, you should.
Let's.
There you are.
Do you see that? Do you hear me? Everything well?
Everything is perfect.
Okay, so hello everyone. Let me somehow continue on this debugging topic, but from a different perspective. And you know, for past I don't know, maybe even 10 years, I was working on VMs, and that actually in my case mostly means debugging when they went wrong. And for most of the time, when the VM goes wrong, or when the system crashes really hard, such as when it does something wrong with the FFI and then it brings down the whole system, I was using GDB, and I have a feeling that among the Smalltalk community, using a GDB is considered like a thing of a last resort. Like if you cannot do anything, then you just do a GDB. But there is very few people who actually can understand, and using a GDB is maybe some people even think it's pointless because you don't see anything. Well, that's not entirely true, and some of you were in Cagliari 2018, and then also in Salta. When I gave a talk on how to use the debugger, I approached the talk in a similar way Boris did just right now. I just showed a real debugging session I had some time ago, showing that using a GDB itself actually can be pretty convenient, and you can see a lot of interesting things, not just some random addresses and memory dumps. And yeah, I've got some positive feedback, but also I've got messages like, and the last time I have heard that was like 2 months ago from Pocho, saying like, yeah, Jan, well, this is all nice, but how does it work? It's nice that you can do it, but for me it's useless because I can't do anything with it. I don't really understand how you do that. So in this talk, what I'm going to do is to show and briefly describe what facilities or what support is there in GDB to support dynamic languages, and how you can build a reasonably convenient support for debugging the VM or the whole Smalltalk system inside GDB. And I mean, not only during the development, but I've been using it even for cases when people came to me and said, well, this system, the application of ours, is just crashing, just disappearing on a production on this particular machine, not on anything else. And can you have a look at it? So it's not only for developing the system as such, but also debugging these sort of strange intermittent problems. So what I'm going now to describe is not like a future. That's more like what is there in stock GDB right now. I mean, if you go to the GDB side and you download the GDB and compile GDB 10, 11, most of this should be there. So this is the whole anatomy of the thing, and we will go through every single bit in more detail. By the way, this fish is actually a GDB logo. Very few people were actually aware of it. Not even I just figured it out when I was looking for a picture for the talk. So the first thing, if you want to support your debugging, your dynamic language, the first thing is, and especially in Smalltalk, is to have a solid representation of the objects and heap, because in most Smalltalks, the runtime structures, I mean classes, methods, and so on, are also the user visible objects on the user heap. This is not common for all languages. For example, in Java, these two are separated. It has its own reasons. It's a different design. But in Smalltalk, this is crucial, because without that, you don't really, you can't really do much. So once you reify inside the GDB using some Python code, once you reify the object and heap model, then you can do and write some pretty printers, which are essentially, think of them as a print strings of objects, but these print strings are produced by the GDB, while the debuggy, the system you are debugging, the VM or the whole Smalltalk, is unconscious. It's stopped, and it doesn't executing anything. This is all executing inside GDB, reading the debuggy's memory and so on. While you have pretty printers, you need to have some knowledge about the code cache, where the code cache is, where the methods are JITted, what are the addresses, which address belongs to which method, and you need to organize this in the tables so you can search it quickly. Once you reify the code cache, in case your VM is jitting, then you might need stack unwinders, which is the thing that understands the Smalltalk or jitted stack. And with that, you finally implement frame decorators, which is the thing that gives you a nice backtrace inside the debugger. And once you have all these pieces, then you can automate a command task using custom commands. And if you are really adventurous, you can put a bit of a glue code to integrate with a BDB, which is a sort of a UI interface and library for GDB and on top of GDB, so you can see more than just the terminal, and you can see more things at the same time, not only one. Okay, let's go in more details over one, over every single one of these. I won't show you the code of the object and the heap reification right now, because it's quite a bit of a code and you need time to digest it. But tomorrow, in the second part of the hackathon, I can show you with the code. I have an image in which you have all these scripts, and you can browse through the code and you can play with it. Here I will just show you what it gives you and how it looks from the user perspective. So, do you see my mouse moving?
Yep.
Yes, we do. Okay,
so I can point. Excellent. So, normally, I have just stopped. In this case, as I'm showing all these examples on OpenB debugging support I did recently. So without any sort of special support, when you ask GDB to print a method, you just get, it's an object, but you get object for pretty much everything that is on the heap. So the type here doesn't tell you much. And the OOP, which is essentially memory address. But you start with that, and then you build an object model. So there is a function in which you pass the name of the object, or you can pass the OOP as a number, and you get a Python object which already itself can print. This is labeled with the prompt VDB PI is a Python. The PI is Python interactive. So you have a Python reification of the object, and you can ask for it byte. You can ask what are the slot names or instance variable names, and it goes and traverses the object memory
the classes and go into the instance variables slots and then traverse the separate class to get the names of the slots of the separate classes. We all know how to do that in Smalltalk, except now we're doing in Python in pretty much the same way. It's just the language is slightly different. We even can navigate through the instance variables inside the debugger in a nice way, so you don't have to use indices and things. You just refer by name, and then again the machinery reads the memory, does the pointer chasing, figures out the correct offset, and gives you verification of that object. So that's the basics. that's the very basic, and you build the rest pretty much on top of this. Okay, what is the rest? Here are the pretty printers. So here in the down in console, you see now when I wrote and implemented the pretty printer, then when I say the GDB print me a method, it gives you, the OOP and tells you it's an instance of a native code. Obviously, you can print more if you want, or something else. It's up to you and depends how you implement the pretty printer or the print string, if you like. Compare it with the original output of GDB here, right? So I think we agree that this is much more useful than just having the OOP. If you are using some user interface, in this case MyVDB, but similar should work for the CDT from Eclipse, even though I didn't try it. So you have a nice Smalltalk-like inspector, so you can navigate through the object graph. You can double click here and you see that the selector is actually a symbol. So you see that the print string depends on what the class is. You can be infinitely creative here. Okay, we have a pretty printers. The next thing is the code cache and symbol tables. Again, this is a support structure for what will come next. So here we have a function in a Python, ls, and you can give it, for example, a program counter, and ls stands for list symbol, and list you all symbols which matches the program counter. So in this case, it will give you a method symbol, also tells you, this method symbol takes 2 arguments, has no temporaries. The code starts at this address, and its code is 35 bytes long. You can also say, okay, give me all symbols which has yourself in the name, and then you get the symbols as a Python list, and you can manipulate it further. As we see, this is a Python list, and the symbol has a reference to the method, which is the heap object, and you can work and use that in your Python code. So this is a support structure we will need right now when we are going to stack unwinding. And as you can see, this is a real beast. This is something that can really bite you hard, and it did bite me many times. And here I'm not going to show you what you get, but rather a tiny excerpt of the code of the stack unwinder for the B I wrote recently, just to demonstrate the complications here. The problem is normally when you unwind the stack, for example, in a VM, when you, for example, do the GC or you need to reconstruct the stack trace, then you might think, yeah, that's fairly easy because you just wall the frame pointers and that's it. But the thing is that when you are doing this in the VM, you are always doing it at the safe point, not at any point, not at instruction granularity. Whereas if you are in debugger, obviously, you are in a debugger because something goes wrong. So you need to be able to handle cases that you are at, stopped, that the process is stopped at any instruction, not only at save points. Sorry, at save points. Right. So here, this is just a small piece dealing with Prolog, right? Because when you are inside the Prolog, then your frame might not be fully built. So you need to compensate that. And the same goes. And you need to know where the epilogue is. But that's not all. Then most VMs, they have this, a method that has frame, but also methods like the leaf methods, like for example, simple getters. They have no frame, so and still have a code. So you need to handle the frameless methods as well. And then there are actually more different methods because you have a callbacks from FFIs, and these callbacks they expect the called function to use the system calling convention, not the JIT calling convention, which is usually different. So you have to accommodate that. And now, well, what if you are supporting more than one platform? I mean, not more than one ISA, and the whole thing suddenly just explodes. It's really complicated. It's a biting beast. So here you have to be really careful. But if you manage, you are rewarded. So you have a proper stack trace. So what you see here, also in the user interface of the VDB and so down there in a normal GDB console, is that if you ask for the backtrace, you see that the Smalltalk frames are properly unwound. So you see, okay, we are in the send side underscore dispatch on, and then we are in the kernel. In the kernel entry point, which is like when you transition into the Smalltalk code, then you get into this entry point. And below that, we will see there is a launcher launch. That's a C++ code, because the OpenB uses a launcher, which is just a little binary that loads the image segment into the memory and just jumps in the entry point. So here you see, if you have the stack unwinder correct and fully working, you see meaningful back traces, including both the native frames, the C++ frames, C frames, and the GTIT frames in a single logical backtrace. That I found is very useful. Okay. The last thing I'm going to briefly describe is that you do a lot of things. For example, I found myself doing a lot of method disassemblies. So looking how the code of the particular method looks like. And normally what I did before is like I use this ls lookup symbol to give me the symbol, and then compute the starting address and the end address, and then use the GDB command for disassembling a piece of memory. But I was doing so often that I actually write a custom command, disassemble symbol, which I can give either a PC or let it take the PC of a current frame, or I can even give it a regular expression to find me the method matching that regular expression, because I was just using it so often that I found this useful. So you can build these custom commands for tasks that you do very often, or even not very often, just during a particular debugging session, and that helps a lot. And obviously, behind the scene, it uses the object model, the symbol tables, and all we talked before. Okay, so this is briefly the individual pieces and how they fit together. So now I hope you get a better idea what is already there and you can use. And tomorrow, if there is an interest, I can show you, I can give you some examples, I can give you, a code to test on. And when I was talking about it to Pocho, then Pocho was interrupting me every now and again, like, can we do that? And can we do that? And I usually said, yes, we can. We just, we need to sit down and write a piece of a Python that does it. And I think all these makes a great options for tomorrow hacking and having fun. Before we go to the question, 5 minutes or how much left, I don't know. Let me share a few tips and tricks I gathered over the time I was working with that, which were not completely obvious at me at the very beginning. So the first thing is treat the debugging code as any other code. That means, you write it nicely, you document it, you version control it. I do even write tests for it. So the debugging code is a code as any other code. Then there is a really great Python interactive command inside GDB, so you can prototype your commands, or you can do ad hoc analysis using the Python API while debugging. This is very, very useful. I already said that having a solid model for traversing the objects that handle all exceptional cases, like if you have a memory corruption, you have to handle it and things like this. This is especially in Smalltalk essential. So my advice, based on mistakes I did in the past, just don't cut corners in that particular bit. I did cut them, and it has bitten me. And the other thing is, it's more like a design thing, and not about just the debugging support, but also about the runtime. Is that I realized that when you are designing your runtime, it really helps and makes sense to design it with a debugging support. I mean, out of process debugging support, as opposed to standard Smalltalk in process debugging. I'm now talking about out of process debugging. It makes sense to design it such that it is debuggable, or it provides all the information you need for out of process debugging. And I would even go as far as saying, if you need to make a choice between performance and debuggability, these days I would choose debuggability over the performance. Obviously, if the performance is going to be really bad, I mean unusably bad, then there is no point. But if it's just a little bit, or if it just shows in the synthetic benchmarks, I just would go for a code that you can debug, because the code that you cannot debug, I somehow tend to think it's a bit useless, because just hoping that you would do it correct never worked for me. Okay, that's all. If there are questions, then please ask. I'm happy to answer if I know. Okay.
Yeah. Have you? I mean, one of the things in watching your talk that's very familiar is having met all of those issues within the COG simulator environment. So dealing with frames that are partially in construction, so that the frame inspector is robust and will, when pointed at a specific frame, will say, okay, there's no valid frame yet until the frame is built. All of those kind of things. Those are things that we deal with too. But the experience that I have in developing the tools with the simulator in Smalltalk is the immediacy of the feedback. So you're debugging some issue and you add a tool to push it forward, just like Boris did in capturing the stacks on each gen. And it's very fast to do that. You're providing, you're using a prototyping environment inside GDB built on Python, which gives the same kind of thing, but you're still at one remove. I wonder, have you thought about trying to build a remote object system such that you can program the Python from Smalltalk automatically, so that you'd be in the Smalltalk environment and you'd be injecting dynamically generated Python code into GDB rather than using the GDB Python environment as your development environment?
Actually, I have a plan to start doing that tomorrow. Like in the hackathon tomorrow.
I was, yeah, that's great. And I thought about that as well. You know, there is a lot of things that, especially in case of B, in my debugging scripts in Python are just, you know, sort of a copy pasted and can be, you know, generated or automatically derived. At this, first of all, this debugging support or this work, and you know, there has been quite some work that I did on the GTB side that already got into the GTB to be able to do these things, and a lot more will come, I hope. But when I started with this years ago, then I started with a Smalltalk XVM, which, as you know, is just a C++. So you know, the COG approach wasn't quite an option. The other thing is, you know, how the COG simulator deals with things like you call into the FFI. For example, we had a really, or I had a really funny crashes inside the Z3, which I was only able to fix when I run it in the GDB with all the support, so I could traverse into the Smalltalk and, you know, inspect the Smalltalk objects and see what values it was actually passing, and you know, where the values came from, to the really interesting optimized C++. So you know, that was the motivation. So this is also for debugging a lot of other things, and you know, real applications which use a lot of external C code. I don't know whether it answers your question, but yes, generating somehow the parts so that the Smalltalk part of it, or the Smalltalk definition of objects is in sync in what is loaded in Python. That's definitely on the list. I haven't done it yet because so far I'm still figuring out how to structure the code. What is there in terms of you know, being robust and handle cases like, you know, memory corruption or things like this. But yeah, definitely that's the way to go. But not yet. Sorry.
Okay, Damian also has raised his hand, so if you can ask now.
Actually, you just answered my question. I tried to write it in the chat, but it seems like it was impossible to send my message. But my question was about generating the GDB support code from the VM, either the VM code or the simulator in Squeak or in Faro.
You can generate part of it. There are some bits which I'm not sure, but yes, that's the way. Yeah. Any other question? Okay, thank you for your attention. Oh, sorry.
Oh, I was mute. So let me share my screen again. Okay. I sometimes think that this should have been called the virtual machine hackathon because it's virtual through Zoom. We are talking about virtual machines, but it's not only virtual machines. We are talking about virtual machines everywhere, like simulators, different kind of evaluators, debuggers, everything is virtual here. So this is a triply virtual machine hackathon. Okay, so I'm going to talk about the open source B. B has been open source on 17 March this year. It's been a long time. It's been like more than 6 months. And yet we are still doing our first steps with it. There's a reason for that. When we open sourced B, we wanted to do some major changes to take advantage of the opportunity because the open source B doesn't have to comply and execute any stuff yet. So we don't have to be in production for someone or something like that, so we can make big changes. And it was the opportunity to change some stuff that in a self-hosted environment are things that are hard to change. So we wanted to take that opportunity. And in order to do that, do I change the slide? I don't know. Oh, there. In order to do that, whoops, this is not working. But there we are, more or less. What do we have? So when we open source VDMR, we put it in Nocerna's repository. And then we started working on what is called the bootstrap, right? What is the bootstrap? Well, what you see here is a screenshot of the source code in GitHub. And what we have here are some folders that represent or that are going to represent modules. And then what we see in the folders are files that represent classes, right? And the classes there are in a format very similar to what to that of Tunnel. Actually, they can be read by many tools that that work with Tunnel. And well, this is just a bunch of characters in a file system, so you cannot really execute anything of that. And so, well, how do you get to get a real Smalltalk from all this? That's the question. And of course, as always, the answer for that is to bootstrap. I think I've been bootstrapping system for like a decade or something like that. So what I thought was that the easier way to show how V is bootstrapped is to make a demo. And so what I'm going to show, it's in another window, so I stop sharing and share again. There should be more windows here to be shared. Okay, I think I'm going to share my whole desktop. There we are. And what we see here is a FAR environment, which is a working Smalltalk that we are going to use to bootstrap our little V DMR. And what we have here is an object named virtual Smalltalk image that is going to represent what are the things we put in our little Smalltalk, right? And this virtual image is going to be generated from this kernel specification, which is the bunch of files that I showed you a moment ago that are stored in the GitHub repo, right? We have a module called kernel that has the minimal amount of things needed to have a Smalltalk working. It doesn't even have file system stuff. Everything like that should be loaded afterwards. And here we use a ring metamodel to be able to work with all those things. We are inspecting this specification, and we can see here that we have a lot of classes which are not really the Faro classes, but are the classes in the BDMR, right? This is a kind of abstraction that models the contents of the module in a similar way to classes, but that that you cannot instantiate, right? You cannot create a new instance of behavior because this behavior is just a specification. You don't really have a class for instantiating this. And well, so what can we do with that is to generate a small bunch of objects that are going to be the Smalltalk, that are going to create the Smalltalk image, right? And for that we have tests. So what we do in tests, here we have virtual Smalltalk image test. And for example, well, we can test that we create an image and that image has, for example, any nil object. If we see the setup of this class for these tests, we are going to specify the word size because, well, we have to specify what are going to be the sizes of integers mainly. And then we can do this genesis. And we are going to debug it. So what does this do? Okay, we are going to set up, and then we are going to get into the genesis, right? This has to do with the original self work, and the work they did was to generate a small self image, and this is very similar. So what we are doing here is to create a couple of objects that are going to represent the objects that are going to be in that virtual image. So I'm going to step over all these and inspect some of them. So let's inspect nil object. What we have here is an object of type slot object map. So this object is a description of what the object in the virtual image has. So this virtual object will have a behavior. It has some specification, which is the ring specification used for undefined object. And it has the slots, which are the elements that we are going to put into nil. Well, nil is an object that has no slots, but you see the case for example, arrays or whatever you have, right? And so the slots can only be objects or type object map to. And after you have done that, we are going to create all classes. Let's step through them just to see how we create one of them. And again, we are going to do a very careful work about not only creating the class, but creating the meta class and creating the behavior, which is a thing that links, for example, classes with meta classes and instances with their classes. And as everything here is recursive because of the meta recursion of the Smalltalk system, we have to be careful and first create all these classes, meta classes and behaviors, which we are doing here. We are not initializing anything else but the classes, meta classes and behaviors. And after we have finished that, then we are going to build those classes, right? So we are getting out of this method. Now we have the instances of those classes. We have to do some fixing just because of the circularity. And then again, we get here and we build the species, right? And now we have, well, we have to be careful with proto-object. This is all this branch does. And then we are going to initialize each class, right? And to initialize the class, we have to set the superclass, we have to set the subclasses, the format of the class, everything that the class has is specified here. And after we finish the genesis, we have an image that can be used for very simple tests, right? This image has only the meta model. It doesn't have any method. We are going to create methods afterward, but from first step, what we want to do is to just check that, for example, Neil has a class named undefined object, and that the superclass of object is proto-object, or that the superclass of proto-object class is class, and that kind of things, right? We are just doing small tests for all that kind of things. Well, and what can we do with that small image? Well, after we have a small image, we can have a virtual machine, which is called a virtual Smalltalk runtime. And here we have a test. And what this does is to let you send messages to the virtual image that we have just created, and to evaluate that messages using the specification that you have in the ring environment, and creating object maps for that. So what we do is, again, we create the image, we create a runtime for that image, and then we just start sending messages, right? For example, here we have that the runtime is sending the message yourself to Neil, and we expect that the result is, again, Neil, right? So let's debug this test to see how it's working. And here is how it starts to get more interesting. Debug test. So we are going to get into this. It's the message without arguments and not sent to super. So what does it do? Well, there are some special messages in B, so those messages are dispatched statically. This is not one of them. And what we do is to go find the behavior that, or the class, if you want, that that has the object that received the message. We are going to do some lookup, and the lookup is going to give us a method, and the method is an scompile method, which is an object living in the Faro image that represents the compiled code for the yourself message, right? And if you see here, you are going to see that, well, there are some special things. Most of the things are living in Faro image, but we have that the class of this compile method is a virtual class. Why? Because the class where this is going to execute is in the virtual Smalltalk, right? So the class cannot be a Faro class. And it also cannot be a ring environment class because you have to add some state to the classes to make them work. So this virtual class has the specification for the ring environment, and it also has the object that represents that class in the virtual image, right? So this method that we just created has like a dual behavior. In some places it has objects that belong to Faro, and in some places it has objects that belong to another world, the world of the virtual image. So what can we do with this with this method is that we can execute it. And here we have something that is pretty interesting, which is that the compile methods that we are creating do not have bytecodes, but they have what we call AST codes. An AST code is a low-level abstraction of the AST, right? When you are executing a method, well, you could just evaluate the AST, but evaluating the AST would be a little bit slow and a little bit bloated, especially if you want to have the AST cached. So what we do is to have these AST codes that represent the AST but are much lower level. What you see here is that we have an encoding of the yourself message that has, for example, an integer, which is a code for message node, and that message node has an array, which is the contents of the method, and that contents has a return statement and it references some variable which probably is self. So what we are going to do is to execute this AST code, and for that we are going to get over this part. We are going to create an evaluator for the method, which is going to be very similar to a stack frame when you are working with an interpreter or a JIT compiler. We are going to place everything there, and we are going to evaluate it. And to evaluate it, we are going to ask the method for the S expressions. So what does it do? It goes to the AST codes, and it encodes all the AST codes into a higher level abstraction, which are the S expressions. Now we are going to see the result. Oops, I think I did it too fast. Here we're going to visit the method, and what we get from the S expressions is this, right? This object is an S expression, an S method that has statements, and the statement is there is only one statement, which is a return, an S return, and that S return is a local return, and the expression is an identifier which corresponds to self, right? So we have the abstraction of the AST, but at a much lower level. We are going to use the same, or we are using the same for the JIT compiler. So, well, if we visit this method, we are going to execute it, And if we receive a message, if we see a message, we are going to create another frame and we are going to evaluate it. And we are going to do all the virtual evaluation of this thing until we get another object, right? Or maybe the same, because in this case, what we are doing is to receive the same object that we created, to which we sent the message. So when we see the result is an undefined object, which is also called nil. And so this is the kind of assertions we do here. And we can see here that we can do a lot of different tests. And well, to evaluate all this code, what you need is to, of course, be able to visit all the nodes of the S expressions, and also you have to create some primitives, for example, for plus, minus, things like that. And we are not really needing to do a lot of evaluation, but we need to do some evaluation, especially for initialization of the virtual image when it's really small, and then we don't need it anymore. So we can do a lot of things, and what this is nice for is that it also allows us to test the S expressions even before we are JITing them. And it even let us initialize our modules by virtual execution. And if there's an error, that error will rise here in the safe Smalltalk environment and not at some unknown point when the module gets loaded. Okay, and well, finally, what we can do with this virtual image is to create image segments, right? What is an image segment? It's a binary file that stores all the objects as they are going to be used by the runtime. And those objects need to be stored in some way. And if you have methods, then you have to think if you are going to use another kind of VM, you are going to, for example, a classic VM, you are not going to need to nativize anything, but if you are going to use a dynamic metacircular runtime, which is the case of V, then you are going to nativize it. So what we test here is to create a builder, add the Genesis objects, and then check what the objects are in the segment. After that, we can say, okay, instead of doing that, let's just add the methods to the virtual image and see what we get. Then we can try to actually write an image segment. It has to lay out all the objects in the file and write them. We can also write them at assuming that they are going to be loaded at a particular address. And finally, we can also, besides filling the classes with the methods, we can just nativize those methods for a particular VM. For example, here, what we are doing is to nativize them for the DMR. So filling classes takes some time because it's going to compile all the classes in the method, in the module, in the kernel module. And after it has filled all the classes, it's going to nativize them, right? And let's wait a bit for that. It's generating everything, and now it's going to nativize, right? And if we see what the nativizer is going to do, it's going to, again, passing the image, passing the builder, going to create native code for all that. And well, I think I'm getting out of time, so there's a lot of things to be shown. I hope for the hackathon we are going to work on all that kind of stuff. I will be able to show it to anybody who is interested. This is something that is also very interesting. The DMR runtime will allow to load B as we know it, So it's going to be a self-hosted environment where all the objects belong to the same runtime. The VM has objects that are in the same space than the rest of the objects, rest of the application objects. But you can think about creating a small kernel and loading on top of that a JIT compiler or an interpreter or whatever you want, and be able to implement, for example, a virtual machine for the that is equivalent to the one that the open Smalltalks have. So, for example, you could create an interpreter for Squeak, Quiz, Fire, or whatever. So that's another interesting idea to think about in the hackathon. Well, I think that's it. So if you have any questions, I'm going back to this thing. Whew.
Well, I will do not so much of a question. I hope you can hear me.
Yeah, I can.
Not so much of a question, but you did a comment on my talk. Now I'm going to reciprocate on giving a comment on your talk, Pocho. I think what is astounding about this, or what astounds me when I see this, has to do with what Gilad said at the beginning of the hackathon. We would have to do something radically different and very, very significant. And my vision of this effort that we are collectively trying to do at the hackathon is that this is a very different world than what Smalltalk 80 was conceived in, and what we're trying to do is very different from Smalltalk 80. It is going back to the original Smalltalk, like as Smalltalk 71, but what we need to do and what we're trying to do is we don't just do a Smalltalk VM. What we're trying to build is a computational platform for the future. And when you're talking about a computational platform, it's not. It doesn't stop at the language level or at the VM level. It goes all the way down to the physics. And the foundational principle of constructing a VM has been summarized pretty well. Back in, there was this paper in Smalltalk Report 93 or 94 by Alan Knight. The paper was called the Smalltalk KeyCast Mega Processor. So he was describing, there's efforts about the people who are trying to build some kind of chip that would be this mega Smalltalk accelerator. And the argument is that because we are so small and because of economies of scale, you will always be better off by just taking commodity hardware and putting a software VM on top of that. Well, this is 2020, and this logic simply does not work that way. This is why we have the J extension community in the RISC-V project and other other hardware extensions for accelerating dynamic languages, because now in 2020 we are designing the whole computational stack from the very beginning to the very end. And with a normal Smalltalk 80 arrangement, where you have the VM set in stone, and then on top of that, you can just do in the image whatever you want. it simply does not go far enough. It's not to what I want to do. It is not acceptable, because if I'm designing at the same time, if I'm designing the image, if I'm designing the VM, if I'm designing the chip, maybe I am prototyping on an FPGA, but then I have to think about what are the implications when I'm gonna actually implement the chip on an actual fabrication process. I can be screwed at any point on the way, you know, and it's like you lose your sanity, because it's like if I am doing this, right, I'm extracting this straw out, and it's synchronous, right, giving the mechanics that my hand knows that it's grabbing and the straw is up, and also my eyes see that the straw is up. But let's say the Maxwell's equations have a little bug in them, very subtle, and so now I have lifted the straw is in my hand, but my eyes lie to me by saying that, oh, the straw is still in the mate. Well, what do we believe, the hand or the eyes, right? And this is a situation in which where you have a traditional VM, you just cannot you cannot have your sanity. And this type of arrangement that we have in the DMR is what is allowing you to work at all these levels at the same time. Yeah.
Well, I guess that we are trying to do things simpler, and that always let you go one step further and one step further and one step further. And that's what makes you end trying to design the whole system, right? It's kind of like vice. Okay, so I don't know if there's other question. I guess not. No, I don't see any hand. In that case, we can start with Eliot. Okay, so Eliot.
Okay. Yeah, thank you. So I'm just going to give a summary of the 3 immediate directions that I'm working in. I'm now in a situation where I'm very closely associated with 3D ICC, who are producing the called TURF. We're going to rename it the 3D environment for business communication that grew out of Croquet, which was where the cog work started. And I'm 61 now. I'm thinking about retirement when I'm 70. So hopefully over the next 9 years, there'll be a stable funding source where I'll be able to work in a company that actually wants what I do. So it's kind of fortuitous that the pandemic has resulted in remote communication like this being really important. We're not in any way stable yet. I was brought in basically to transition from 32 bits to 64 bits as the Mac has changed and no longer runs all of the old stuff. the application that's being sold now is basically what it was back in 2012. So we're in this process of navigating to new customers as we bring in 64 bits. It's a bit of a risk, but it feels good to me. So given 3D ICC provide a context in which I could, they started the cog work, they paid me to do the initial cog work. Looks like it'll be a great context to continue the cog work. I'm thinking of the needs of that application. So the basic experience over the past 9 months has been incredibly expensive moving of low-level code, plug-in code that interfaces the system to sound, to various kind of platform integrations for screen scraping and screen sharing, etc., etc., etc. It's all had to be rewritten over operating system migrations, and the traditional approach in the VM of there's the Smalltalk code, and there's a plugin which is kind of an auto-generated wrapper from Smalltalk down to then a middleware layer, which then maps to a specific platform API, for example, 3D sound spatialization or screen scraping or whatever. You've got all of these different levels, and Smalltalk at the top, and there's auto-generated C in the middle, and then there's C++ or Objective-C or Objective-C++ and C++ and C, and low-level debugging, and it's really grimy, frustrating, slow, unproductive place to be. So the most important thing for me is interconnectivity, is getting rid of all of those intermediate levels and moving the platform API, programming directly against the platform API, getting rid of all of that nonsense in between. And so the main problem there is asynchrony, is being able to have non-blocking interfaces. So the thing that I started 10 years ago, having talked with Dave Simmons, is a lock-free implementation of a Python-style VM. Hang on, I just want to share my screen. There we go. There's the button. There we go. Pocho, can you enable?
Oh yeah, sure.
Thank you. So in the Python VM, the architecture is that you can have any number of threads, but only one thread is in command of the VM at any one time, and you only transition between threads basically on an FFI call out or a callback. So this is the one. So and I'm not quite sure what's going on in Lille, but I think that they're going the same way, is that you do this by having an operating system semaphore, and every call out goes through that semaphore. Whereas what happens with Dave Simmons' implementation is that you have a lock-free algorithm where one variable holds the ID of the currently executing thread, and when a call out happens, that variable is zeroed, which implies that the variable, that the VM is unowned. And when the FFI call returns, the variable the value of the variable has been saved locally, so that the FFI is aware of the thread ID of the thread that owned the VM that made the FFI call out, and it tries to test and set the variable back to what it was before. And if it does, then the VM is reowned and computation continues. So the cost of freeing the VM is zeroing a variable, executing the memory barrier instruction, and then on return doing a test and set to attempt to get it back. So it's incredibly cheap. The question is, but how does this actually thread? So in most modern VMs, Java VMs, Smalltalk VMs, the way that you deal with the need to periodically jump out of machine code to check for events is not to have some activity on say, every frame building send, which would be an explicit poll. It's a very poor choice because as soon as you start executing code where the send frequency varies, your polling frequency will vary. So for example, if you have code that's doing a lot of large integer arithmetic, those primitives can take many microseconds, maybe even milliseconds if you're dealing with million byte integers, those kind of things that you're adding or multiplying. So doing something on every frame building send means that suddenly the system will become unresponsive to interrupts or whatever, depending on what you're doing. So what you do instead is that there's a high priority heartbeat thread which blocks for say a millisecond or two, and then does something like in the case of COG, change the stack pointer, the stack limit variable against which we check for stack overflow on calling a function. And so that will cause the next send to break out and call for events. Alternatives are to write a value to a page. This is used in some Java VMs, and then change the page protection so that you revoke write protection, so that the next write you'll get a fault. And the reason for using a write is that because of processors' write buffers, you basically don't stall for a write. You would stall for a read, but you don't stall for a write. And of course, that technique depends on how efficient it is for changing the page protections in an operating system. And so that technique is only used on certain platforms, that kind of thing. So what we're doing in COG is we have a heartbeat, and we change the stack pointer. So the heartbeat is extended to check for the ownership of the VM. And when the VM is found to be unowned, the heartbeat then makes sure that there's a thread in the thread pool and sets it running so that it tries to race to own the VM against the returning FFI call. And if the thread wins the race, then it will pick up the next runnable Smalltalk process and start running that. And if the FFI call wins, then okay, the FFI call returns. So the effect on latency is that if you've got, say, a 500 hertz heartbeat, that on average an FFI call will block for 1 millisecond before the heartbeat will beat and kick off another thread to run Smalltalk. So it's a lovely, lightweight, extremely efficient thing that allows you to make as many threaded callouts and indeed callbacks in. It also works inside plugins. The basic pair of calls is kind of disown VM where you remember the value that disown VM returns, and then own VM where you pass the value you got back. And everything is hidden behind that. So you can put the disown own pair around any potentially blocking thing. Now, there's an issue to do with garbage collection. Do objects move, etc.? So one of the design goals behind the Spur memory management was to provide efficient pinning. And so what the FFI code, or for example, code that does a potentially blocking read, does, where you've got you're reading from a file descriptor and you're providing a buffer, is that the immediately before you do disown the VM, you also pin your buffer object so that the garbage collector won't move it. So what I'm going to show you now is like a little demo of this. So there's a demonstration image that I've been using for some time, where there's a read eval print loop. So here, the blue window is the simulator, and we're running ARM machine code, ARM v8 machine code on a GDB-based processor simulation. And if I type in, you'll see down here, can you see my pointer? Anybody?
Yep.
Yep.
Yes,
So
we do.
you see that down there, it says squeak. Oh, okay, it's moved down. Well, anyway, there was a prompt there, squeak, and so the thing providing the input to this prompt is this input requested box that I'm pushing into, and I hit 3 + 4, and did you see 7 came up here? But you'll see while this is blocked, I can actually go in and interact with the Smalltalk system. It's a bit slow, the simulator. There we go. So what I'm going to do is like just pause this. Oh yeah, I can't pause it. That's right, because I can't interrupt the damn thing. This is work that I need to do, is actually being able to pause the write. Is pause the write process, and I haven't got that working yet. I can't target the interrupt of what I want. So this is working. Working to some degree. It's nice to come back to the code a decade later with some better style, and to implement the thing, clean it up, make it nicer, and collaborating with John McIntosh to deal with the event issue on Mac OS, where you can only get events, GUI events, from the main thread. So the VM has to be split into a main thread which interacts with the GUI just for events, and then subsequent threads which actually run Smalltalk. And then I'm working on ARM on Manjaro and a Raspberry Pi. So the result of this is the ability to then replace kind of all of the blocking socket primitives for name lookup, etc. Make any FFI call potentially blocking, and then the ability comes that all of those FFI calls that are made in the context of a plugin, in context sometimes of a thread inside the VM to provide responsiveness, comes back up, and I can just write directly against the against the platform APIs. So then the next thing is smooth animation. So here's my development image. It's been running for 12 hours and it's been idle for 10 hours, and it's got almost half a gigabyte. And it's done 9,000 GCs, and 11 of those are full GCs. So the scavengers, I've got quite a big Eden here. I've got a 16 megabyte Eden, a 16 megabyte new space. I'm sorry, a 16 megabyte new space. And with that kind of size on my 2.2 gigahertz VM, I'm getting 1.6 millisecond pauses. And then the code zone is quite large too. I think this is like a 3 megabyte code zone. And with a 3 megabyte code zone, compactions are very infrequent. You see that we've only done 31. So it's kind of one every 5 minutes. I think that's right. Yeah, one every 5 minutes. But they do take quite a long time. They take two milliseconds. So you can trade time against total performance here. If you make the code zone smaller or you make Eden smaller, you get lower pause times, but overall you get more overhead. So it's a difficult balancing act. But basically, if you think about smooth animation, we want kind of 50 frames a second would be nice. So we've got a 20 millisecond budget. So one way to conceptualize this is that you want an application that spends no more than half of your entire budget. So everything that you need to do, you can get done in, say, 10 milliseconds, which leaves you 10 milliseconds for the worst case of the coincidence of all of these potential pauses. A pause from reclaiming the code zone. And you reclaim the code zone. The JIT is JITting methods, Smalltalk methods into machine code on demand. And if your working set changes, you may fill up your fixed size zone. The advantage of the fixed size zone is that it's very fast to enumerate over methods and patch, etc. Instead of things being scattered over memory and growing without bound, which introduces unexpected latencies later on. So the fixed size code zone will need to throw away methods when the working set changes, and choosing a size where this doesn't happen too frequently and the pause time is acceptable is kind of the game. And so what we found with the TURF application, which is a big complicated application, is that kind of a 3 megabyte code zone does fine. So okay, on current hardware, we can look at kind of 2 millisecond pause time as an upper bound for code zone. We can look at say 2 milliseconds, 1.5 milliseconds as an upper bound on scavenging. And what we need to do is to bring this relatively gigantic pause due to full garbage collection down. So in a full garbage collection, we're doing a scan mark of all of our work. Well, in fact, we do a scavenge to empty Eden, and then we do a full scan mark of all of the objects in our old space, and then a complicated planning compaction algorithm. It's a 3-pass algorithm where every object that's going to be moved copies its first field into a buffer size, and then updates its first field, which is in Spur of potentially a forwarding pointer, to point to where the object is going to go. And then you make a pass through all of the objects and update all of the pointers so that they follow that forwarding pointer. And so now all of the pointers in all of the objects are pointing where they're going to go. And then you make a move pass where you move all of the objects and you restore the relocated first fields. So the scan mark is like a 60 millisecond average, and that planning compaction is like an 80 millisecond thing for something which is basically 2 orders of magnitude bigger than what we want. So the point about the Spur memory manager, just to recap very briefly, is that it does lazy forwarding. It basically arranges that whenever you're fetching the instance variable of the receiver in a method, that object is never forwarded, so you never have to check. But any other object that's been forwarded, because you've done a become or whatever, you may be facing a forwarding pointer. So if I want to do a become with 2 objects, I'm going to stop sharing my screen, and I'm going to use my hands. So you've got 2 objects, and you want to become them. You create 2 copies, and you turn these 2 objects into forwarding pointers to the copies, and you change the class and the format information on the original 2 such that they don't understand any messages. So whenever you send a message to something that's a forwarding pointer, the message send is going to fail, and on the lookup side, not the fast high performance cache side, but on the slow side of method lookup, you're going to check the current frame for forwarding pointers and follow them, changing any pointer that refers to an object which is a forwarding pointer to the object that thing points to. So you eliminate the forwarders, and then you retry the send. And when a primitive runs, primitive has to validate its arguments. It will fail validation for any forwarder, and so primitives, if they fail, they check whether their arguments contain any forwarders. They fix up the forwarders in their little part of the object graph that the primitive touches and retries. And a nice thing is that the computation of how much of the object graph do we need to touch is computed automatically by analyzing the source code of the primitive and figuring out how much of the object graph it touches, and turning that into a number. And the object graph is traversed to that depth automatically on primitive failure. So whenever you do a message send, or whenever you invoke a primitive and forwarders are involved, things will be fixed up. So then the other part of it is that the stack zone, which is where we're holding our most active activations, because we don't hold things in context, we hold them in stack frames. The stack zone is a small number of pages, maybe 70, 100 pages each, kind of 2K each. And we completely scan the stack zone after each become, so that the receiver pointer in each frame is never a forwarding pointer, which is why we don't have to check on most things. So the whole idea of Spur is to give you the kind of flexibility of forwarding pointers, but there is no read barrier. There is an implicit read barrier in sends, and there's an implicit read barrier in primitives that you would have to do anyway. So you're like hijacking an activity you have to do anyway. So the coming back to the garbage collector, the traditional solution to the scan mark part of the problem is Dijkstra's 2-color marking algorithm. And I won't bore you with that, but basically, straightforward. The notion is that you monitor stores into old objects, and if you're storing into an object which has already been scanned, has already been visited, then you've dirtied it and you put it back on the list, and the process of scanning continues in parallel with Smalltalk until all of the objects have been categorized into fully black, where they're fully scanned, and white. So that's a well-known algorithm. Over recent years, the Lua community did a really nice variation where at the end of a scan, instead of you resetting the 2 bits which define these 3 colors, you just rotate the sense of the bits, so that at the end of a cycle, then the bit pattern rotates, and you've reset it for free. So that's well known and straightforward to implement. What Clement and I designed was that we realized in Spur we could do incremental compaction. And Clement wrote a nice paper, did a validation of this with 12 to 16 gigabyte heaps. And the idea is that in Spur, the heap is M-mapped gradually in segments. So when you start off, you have one big segment and one free segment, and then as you continue, you add new segments, and the new segment would have like a minimum size. So 16 megabyte segments is a standard thing, but if you allocated a gigabyte object, you get a gigabyte segment. And the segment manager holds a list of the segments in density order. So at the at one end is the segments that have the most free space, and at the other end is the segments that have the least free space. And we either allocate some new segment, or we choose the least allocated segment as our target, and we basically do a series of becomes from the least occupied segments, where we become them into one segment until we fill up that segment. So now we have one full segment, and all of those partially full segments, they're not empty because they have forwarding pointers left in them, right? Corpses, but all of those forwarding pointers point to the objects which have been compacted into that segment. And then computation continues, and any message sends which go to those forwarding corpses will get forwarded, and the performance overhead is less than 1% of total execution. So with this kind of approach, we can do as much compaction in a step as we want. We can compact, like, even half of one of those empty segments. So we can tune that to give us the pause times we want. So with Dijkstra's 2-color marking and our Spur incremental compaction algorithm, we can tune old space garbage collection pauses down to the same kind of order as scavenge and as scavenging and method zone reclamation. And so we can get the worst case pause time to within 5 milliseconds, and therefore make the platform suitable for smooth animation. So there's a third direction, which is kind of my PhD, which I'm not going to talk about much. It's just about improving register allocation within the CogJIT. And that's actually taking a back seat to these other directions right now, because this is much more relevant. This kind of one of the experiences, the constant experiences over the past few years, has been that you have these great plans, and then real life intervenes, and you just have to put them on the shelf and keep on making progress in the like rolling downhill, the path of least resistance towards towards the gravity sink, where you're getting the potential energy that you get when you roll downhill. Okay, I'm done.
So much work, Eliot, about performance, and it looks like this phrase that usually is made for hardware, that software is getting slower faster than hardware is getting faster. It also applies to virtual machines, right? It's like you always have to be making faster VMs because the software is getting slower every day.
You want to do more and more. I mean, one of the sad things, you had the experience as you were demonstrating, is that you clicked the debugger too fast and you had to go back.
Yeah.
So people in the Squeak community did exactly the same thing in the debugger, which was to change the debugger so that the variables are highlighted, so that the ones that are out of scope are in red and the ones that are active in green, etc. And it's fabulous. It really does give you more information. But the implementation is so bad that as I'm clicking through slang generation or whatever, I can get in the future.
In the future, yeah.
And so, yeah, I think it was one of the extraordinary things that Dave Unger said is that, whenever a computer makes you pause or makes you wait, it's a crime against humanity. I mean, he was quite emphatic about it. So yeah, it's not necessarily that things need to be faster. I mean, we're using Smalltalk, and we're probably 2 orders of magnitude slower than C++, and we're definitely at least an order of magnitude slower than fast Java VMs. But we do want the right kind of performance. So being able to thread freely and being able to control pause times, those are 2 demands that we have at Turf that we've got to meet. And I don't know. It is a bit of a habit, isn't it? Optimizing, yeah. But it is a lot of fun. So.
Okay, so I think that Clement should start now. We are already half an hour late. We have been getting 5 minutes late and late and late. Oh, so Jan has a question? Oh.
Yeah, I have a question, Eliot. The GC algorithm, the fast compaction you just described, maybe that was the paper you referred to, but this is remarkably similar to what I think Bacon described in some paper. I forgot the name. Sorry, I'm really bad at it.
Yes,
but this is actually...
That's right. But there are lots of differences. The treadmill is fixed size objects. Every object is the same.
No. They did this. They did this inside J9. I believe this algorithm is also in the OMR right now. If you implement the proper interface and blah blah blah. But they did pretty much the same thing, except they did not use the lazy forwarding. Except they designated the evacuation area, so the area where they want to get rid of the object. And while they were scanning, they were remembering all pointers into that. So after actually evacuating the whole area, they patched the pointers.
Right, and so that's a big difference, right? Because we don't have to patch; that happens implicitly.
You don't have to patch, but then you have to wait until everything gets out before you can actually reclaim the page and give it back to the OS.
But it's perfect, because when you're using the 2-color algorithm, you've got a clock that is continually cycling, right? So you know, after 2 cycles of that clock, as the scan mark does its job, it also fixes up forwarding pointers. So after 2 cycles, you've reclaimed everything that you did 2 cycles ago.
Okay, this is the point I missed. Okay, thank you very much.
Sorry about that. I should have said that, right? So the scan mark, the incremental scan mark, as it scans an object, it is following all of the objects, right, to mark them. And so as it follows them to push them onto the mark stack, if it's a forwarding pointer, it follows the forwarding pointer and changes the referent. So once you've made a complete scan, all of the forwarding objects that were created before the start of that scan have been eliminated. So there may be new forwarding objects that have been caused during this scan, and they won't be reclaimed until the next scan, right? So we're always we've got 1 scan's worth of forwarding objects to clear, but we're always making progress.
Yeah, that makes perfect sense. I missed that little detail. Sorry.
No, you didn't miss it. I forgot to say it.
Okay, guys, sorry to interrupt you. I guess we are getting a bit late, so we should continue. Thank you, Eliot. Hello, Clement.
Can you hear me? Or
yeah, we can.
Can you see me? Oh.
Yes, we do.
Okay, so first I'd like to say I'm happy to see some joint effort on the VM and Smalltalk VMs. Before I used to be in research, and I did mainly like my own things because I had to push for papers and stuff. But I really hope like you managed to do something and stay together. And the more I work now, like as an engineer, I think like, you know, it's better to do a small incremental effort on a shared code base and going slow long term as a team. So yeah. So I have little time to put on the VM and the next 3 years. A few small things I want to do, and I will try to do things. But yeah, so that's great. So I'm not going to talk about what I do now because I work mainly on Java specific optimizations. So I decided that for this talk I was going to talk about more like a retrospective and like what we did with the Sista project and what worked well and what didn't work as well. So maybe I didn't understand the concept of hackathon, but I made some slides. So I will try to share. Yeah, can you see that or?
Yeah.
Does it work? Yeah. Okay.
It works.
Yes.
Okay. So I wanted to step back on the Sista design, the in-image JIT, and I'm not going to talk too much about like what's a JIT with optimization and stuff like that, but more like what we did and what worked and so on. So first, some kind of retrospective. So Sista stands for speculative inlining Smalltalk architecture. The goal was to build an adaptive optimizer for the Open Smalltalk VM to gain performance. What we managed to do, what we managed to build, is some infrastructure where like a range of benchmark went like between 1.5 and 10 times faster. We built some foundation for live coding in the sense that we built some support like for installation, modification of method at runtimes, debugging, and so on. And it was not complete, but it never reached production. I don't think it got at a point where it was very usable. I used it a bit, but we've also not worked on compressing the optimization metadata. So yeah. So we started from Cogit, which Eliot built, which is a JIT which compiles like the compiled code, which is generated in the Smalltalk image by the bytecode compiler into a native function, and Cogit is already doing like all the mapping to machine code. And what I built is like inside the Smalltalk image, and that's something I will discuss afterward. Some kind of compiled code to compile code optimizer, which compares to an extended bytecode set and which managed to do a Smalltalk specific optimization. And it was a nice idea because we had the optimizer like in full Smalltalk, which was easier to build. The optimized code could be persisted across startup in some way, and all of that was nice. So the in-image JIT, which is called Scorch. So it took me like I think 3 complete iterations to get it to run and to get it to de-optimize correctly and to get it to speed up code execution. So it's SSI compiler, and I think what I struggled the most was like to design a good like intermediate representation. It's not that it's hard. It's just like I think it's better to have advice from someone who has built optimizing compiler before to design a good IR, because once you're started with one, it's difficult to like change it too much. And so I think the things I struggled the most with was like the encoding of all the optimization metadata and how to recover from there. And also the other thing was like what to preserve across optimization. So we typically had like a def use graph. So like each instruction would track like which other instruction is using the result of that instruction. Sometimes we need to build the dominator tree to prove that some instruction is necessarily executed before another one, and all sorts of optimization break all these graphs. So yeah, so it's difficult. So on the compiler I work now, for example, we maintain like the diffuse graph all across optimizations, but not the dominator tree. So yeah. So what we managed to do, so this is the relative speed up I had at the point of my PhD, right? So we managed to improve like benchmark by like between like 1.5 performance boost and 10 times. As we can see, it's mostly 1.5. So one of the only benchmark we got to 10x was because of optimization and small loops. So I wanted to come in to discuss a bit about that. So one of the things I noticed is that 2 optimizations seem to improve performance, while the rest did not do much except from enabling the first 2 to get performance, right? So closure inlining and all the side structure like term vectors and allocated context and so on, so that typically like improve the performance by like minus 33%. And we had at least one benchmark, which was Camins, which was like mainly like many loops in each other, and it was written with high-level iterators like in Smalltalk. Like the compiler will either manage to inline them all or none, and that will give like a 2-3 time performance boost. Yeah. What got the 10x speed boost was like optimization and small loops, and I think that's like what I should have focused on since the beginning, which is basically there was a lot of small loops in the code which do things like copying an array to another one and or checking equalities between arrays and stuff like that. And if it's written in Smalltalk, it will typically go through like many calls and many different pieces of code, like just things like but there is like I don't know, like 50 instructions in machine code, and even if like the actual execution doesn't go through all of them and it jumps around, it's not going to get to the best performance. And if the few benchmark where we managed to get those small loops into like just a few instructions, and I don't know what happens in the processor, but it gets much better, like 10x. Yeah, so if like someone wants to build another like adaptive optimizer, I will focus on this thing. So the main problems that slowed me or us, I don't know if I include Eliot, down. So I think like I didn't have a very good process So when I started, I was not very experienced, both like in engineering and in compilers in general. And I think the main mistake was like I didn't start by being focused on benchmark. And I can see now, like when I work on compiler, I directly like make only optimizations where I have a benchmark which proves that it's worth it. And also, you know, it's just easier to show results to people. It's easier to focus on the right thing, because like I used to look at code and like think, oh, this could be improved, but it will not change performance, or I don't know. So yeah, so if you're building an optimizing compiler, please get a set of benchmark ahead and try to focus on those. I lost a huge amount of time with the closure implementation that was in Squeak and Pharo when I started. I don't think it was possible to build an inliner because of it. So it was really painful. It took a long time to build a new implementation to get it to work in both Squeak and Pharo. I don't even know if they're using it now. It was working at some point in both, and I think tried to switch to it. Yeah, so to get started with the next section, I think I struggled a lot because I had to work with different images. So my setup was like I was paid by the Pharo side. I was working with Eliot, which is mainly on Squeak. And there was lots of compatibility issues all the time. So both runtime are like evolving. Pharo specifically is rapidly evolving often in a non-backward compatible way. So it's difficult like to keep up to date with that, and also make it work for Squeak. And yeah. Do we have, yeah, only 10 minutes. So on the second part, I wanted to talk a bit more about like how do we interface the VM and the image, and especially in the context of Open Smalltalk VM. There is multiple supported languages, and it's a bit unclear to me like how the JIT design that we made, how we could move that to production in a nice way with the situation in Open Smalltalk VM. So I wanted to discuss that a bit. So Open Smalltalk VM supports like Squeak, Pharo, Quiz, and Newspeak. I don't know what's the status of each of them, but like the idea, at least when I did the project, was to have the JIT works for all of them, and it was like it was important for Eliot to get it to work with Squeak. It was important from like the money from like the people who were paying me that it works for Pharo. The initial design we had was like the interface between the VM and the language is only like there is a callback to trigger the JIT, and there is a callback to trigger the optimization. That's it. It turns out that it's much more complex than that. So like an example I can take is because we are like having optimized compile code in the form of like compile method, then in your image you start having in method dictionaries optimized method, and in your stack you start having optimized context. And there's lots of places in Smalltalk where like people directly access things like they will so they would, yeah, they were looking like a method dictionary at the selector, but some method, or like this context debug, right? So it's very difficult to just try to build a layer in between like the language and the ID, and it's especially even more difficult in the context where like there is multiple languages on top of the code. So like if you're trying to build, so if you're not trying to build an interface and directly like patch the ID, like the debugger or the inspectors, then you have to patch it like in Pharo, in Squeak, in all the others. So in the context of my work when I was in Pharo, like the debugger and inspector framework changed multiple times across like multiple years. So that means you need to do it and do it again. And at some point, I had in an old Pharo version like a debugger version working the optimizing context, but that's not the debugger that they use now, and it's different from the debugger that is in Squeak and in Quiz. So if on your own you want to build a layer between like the language and the IDE, and reuse that as like you have to intercept like all the direct access that everyone is using already, which could be in user's code. So yeah, so that's already very difficult. So I don't have a very good solution for that problem at this point. The other thing was like the in-image JIT dependencies. So I tried to build it in a way that it would depend on the least amount of code, but it was using things like arrays or dictionary or stuff like that. And each time you change the kernel now, because your JIT depends on it, it might break the JIT, but it might break it in a silent way. And then what happens is, because like the optimized method have access to unsafe bytecode, you end up with a segmentation fault and you have no idea why. So again, like Smalltalk VM is working with multiple runtimes. I was working mainly with Pharo, which is like rapidly evolving and including like change on the kernel. So it's like really difficult to see like what can we depend on the kernel, what is not going to be changed, everything is going to be changed. How can we build like some kind of layer so to abstract away from like the optimized code and context, because like below there is a kernel which is changing, on top of it there is like an IDE which is changing. Yeah. So yeah, and also like even like the interface between like the VM and the image, like I don't know what's the status now, but at some point Pharo started to introduce like a lot of specific flags in the VM, so that there could be like differences in between like what a primitive answer and so on. So if you're trying to build something for Squid and Pharo, you have to deal with that. So if you're like really planning to deploy the optimizing JIT, right, then like assuming like you start with like one customer, then you have like some kind of business pressure, which like the customer will say, oh, I have this bug, I want you to fix it. And he's likely going to use only one runtime. So then, you know, I don't know how it's going to work, because then you have one bug fix for his problem, but maybe you need to fix like all the different runtimes. And yeah, it's difficult to know like how can we be responsive in that context. So what are the future plans for the multi-runtime support, right? So what many people were suggesting to me was like to build the image JIT for one runtime and make it work. So the problem is, like in my context, as I said, it was not very easy, because I had to pick between Squeak and Pharo, and it was like between like what I was working with and my fundings. So yeah, I think it was like, I can say it was impossible. It's also like a bit hard to decide like what's the message to the users, because like people have been hearing in the past like to use like one specific language and then another one, and so let's say someone builds it for quiz, and then like users might get confused, like why does it work only on one of them? And, yeah. So another solution was like would be like just not to go that way. So there is like a lot of things that we have to do on the VM, which are like maybe more important than improving performance of Smalltalk code. And that would be good, like to focus on simplicity. And I see like in what Pocho was saying, for example, that he wants a simple VM. It would be nice to have something not too complex. So it's probably good enough for most users. So like one thing I wanted to mention is there is one guy that built the Lua JIT. It does adaptive optimization. So at least like it's possible that we have something like that in a shared infrastructure. But yeah, I mean, given our resource. And lastly, like I think like if I was going to continue, I would like probably try, but I will need to convince the other people working in the VM, including Eliot, but to move like most of the code in the VM code base. So currently it's in Slang, and that's the problem, right? So
I think we lost it, or it's just mine.
Did you lose me? Oh.
No, for a couple of seconds.
Sorry.
I think it's my connection.
So so one of the things, if I was to go forward, I think like the direction I would be interested in taking is to share the code base with the existing VM and the image JIT. And so that could mean moving the JIT to Slang. So initially we didn't want to do that because like Slang is not like really super nice, and there is so Slang is like a restricted Smalltalk in which we most of the VM is written and it compares to C. Yeah, so there is quite a lot of complexity in the optimizing JIT, and it's not so easy to express it in Slang. But when I hear, like, for example, that when I see the experiment that you're doing, or like the work you're doing on maybe building something different, so if like Slang gets improved by what Boris is doing or Pocho is doing, I don't know, maybe you know, that's the right way. So if like the code base will be shared and like the optimizing JIT will be part of the VM, you know, that means that we don't have issues with like all the different kernels. We don't have issues with like optimized code and context in the image because it's only in the VM, and there's just one product, right? We don't need to like push a bug fix to 4 different places. I think now after building the initial one that it's possible to build a JIT doing adaptive optimization, focusing on simplicity and just low-hanging fruits. I think if we take the example of a JavaScript core, which is the JavaScript engine for Safari, they've built 2 levels of adaptive optimization, and the first one focuses on like high-level optimization and is not like too complicated, and only the last layer, which also involves a lot of backend optimization, gets like really nasty. So it should be possible to do something in that direction. I struggled in the past because like if I would want to make an update to my intermediate representation in the image, then I will need to change the encoding in between the image and the VM, and that means I also need to change the backend in the VM, and I need to update both like the VM and the image. So that means like if that was going to production, we will need to explain to people how to update things to update the both components at the same time. And also like the last thing was like the biggest boost was on the biggest performance boost was on small loops, and I think like it really boils down to like can you get a specific loop to like a few machine code instructions instead of going through many indirections, and it's not so easy to do that with the current architecture and the indirect representation.
Could you say that again? It's not too easy to do it with the current.
With the current design, because like we have to go through the bytecode encoding and then into the JIT, and it's not so easy to understand like what's going to be generated and so on. So what I started to do in the end was like to add more and more instructions, and like to add, for example, setting an instance variable will be we'll have like 4 parameters, like do you want to do a start check, do you want to do a read-only check, do you want to do I don't know what. Yeah, and there was not even tricolor marking, right? So yeah, so that's I think that's what I wanted to talk about. I hope you found that somewhat interesting. Yeah.
Yes.
I stop sharing. Please, you ask a question, Eliot.
Yeah, so I was making notes. So one of the things you said at the time, and you've convinced me now, is that de-optimizing from optimized contexts to unoptimized contexts should be done entirely in the VM. So then the debugger isn't affected. So the optimized contexts are invisible to the debugger, and it seems, you know, there's lots and lots of effort on debugging right now in the different dialects, and so that makes a lot of sense. What I wanted, I came to the realization that the right way to have stability in developing the in-image optimizer is to use the simulator. So for those that don't know, right now, the first level JIT provides performance counters on if true, if false. And when these trip, you get the equivalent of a does not understand. You get a counter trip message comes up into the image. And so now you're in the image above the VM that you want to introspect into those methods and find out what they're doing, and then create a new method which inlines several methods, and then have the JIT continue. And the problem is that any bugs in this system will affect the compiler that you're trying to implement. So if instead you use the simulator, so that instead of delivering the callback in the simulation, you deliver the callback in the development environment for the virtual machine. So now we have Scorch alongside the rest of the VM, and Scorch is only optimizing the image that's run under simulation. Then Scorch is unaffected by bugs in that. And then we can stabilize. And then from Pocho, it's clear that if we are ever to have Scorch running in the production environment, we have to have a complete set of tests so that any update to the production image can be checked, so that we know that it won't affect the simulation. From Gilad, we know that we can approach that validation essentially in a sandbox before we deploy. We don't have to do it when we upgrade. You just have to have a copy of the deployment system and do the validation there. And then one thing that I still think is worthwhile is this improving the register allocation in the CogJIT. So central to the CogJIT, this is Peter Deutsch's design. The way that you map a pure stack-oriented bytecode to register-oriented code is by having a simulation of the context stack that bytecodes refer to when they say you fetch an argument or push an argument onto the stack. And what you do is every time the JIT sees one of these bytecodes, it will end up pushing a descriptor onto a simulation of that context stack. So the JIT builds up its parameters. We're adding temporary variable 3 to the integer 1 by having a descriptor for temporary variable 3 on the simulation stack being pushed, and a descriptor for 1. And then when we process the scan, we're looking at this. And Clement and I have a design for extending this scheme, which basically just does register allocation at the point of send, to being able to do register allocation to temporary variables, and keep temporary variables in registers using write through to make sure that the stack value is always valid. So it's a very, very, very simple scheme. And that, is, feeds towards your goal of getting small loops in as concise code as possible. So I still don't want to give up this lovely idea of the image, of the optimizer alongside the image. But yes, I mean, the thing was, while what you did was an exercise in frustration, you did actually do it. And you did actually demonstrate that it worked, and this learning that we have about the engineering of it, I think is really fascinating. And if we should write it up in a more official venue, kind of the PD&E kind of environment. maybe we have to do another pass at getting it productized and getting some results. But I think that PDI, program design, PLDI, sorry, and aiming at PLDI, if we really have some good experience to show, I think is worthwhile. I'm still very excited by this, and I'm desperate to, I've signed up for doing a PhD on the register allocation part of it. Luckily, they allow 4 years for PhDs in Germany, so I'm kind of a year and a half in and not under pressure.
So
some states are going to have to start writing.
So you mentioned different things. So one of the things was to move the optimization process in the VM. So having it in the image was a bit annoying because I had these infinite loops where the optimization code would optimize itself and stuff like that. So I had this workaround where any code touched by the optimization code would not be allowed to be optimized. And that meant that I had to duplicate some classes like dictionary and arrays for that. So that's one part of the problem, but I think that's not the biggest one. The biggest is more now we have optimized context in the image, and how do we build debuggers on top of that in a way that that works in all the different IDEs, in all the different runtimes that Open Smalltalk VM support. I think that's a much tougher problem. You mentioned then the developing the in-image JIT with the simulator. So I think I struggled a lot with the incompatibilities between Thero and Squeak, and I think that was given my situation, I kind of had to work with both. So it's clear that the better solution would be to do everything in one of the runtime, and it would be definitely nice to have some support in the simulator. So I don't know if you're planning in the future to extend Strong to something like what Pocho did for B, or so.
It's much more not extending it, throwing it out and replacing it.
Okay. So so the thing is that if you have something better than Strong, right, then there is much less value into putting the image JIT in the language, right? And in that case, you don't have to go through that extended bytecode set where you lose information, where each update of that set is complicated because you need to update both the VM side and the image side and on all the different images. And that means for example, you have your SSL representation, and you can do register allocation while you DSSA, which is much easier, right? So it works with your scheme. It's going to make it easier because now you're building a register allocator with temporaries, but you don't know where they're assigned and stuff like that. And in SSA, you already have all that information. So I think that's, yeah, I mean, there's lots of trade-offs to discuss, right? But yeah, that could be an interesting direction.
Yeah, I think that the trade-offs are fascinating. I mean, I do know where the assignments happen.
Yeah,
I agree.
So is there other question? Yeah.
This is probably completely useless to you, given the context. But this problem of, say, interfacing the problem that everyone can muck with the method tables at the image level when you're actually JITting and so forth. It seems to me that, again, this isn't perhaps practical in Smalltalk the way things are done, but mirrors are a big help here, because you would be localizing this to a particular module that is responsible for this. The other thing that you can do with mirrors is that you can manipulate a different image from one to another. At one point, Ryan actually had this working in Newspeak. I don't think that it works anymore, but basically you can do all your work in one development environment and have another development environment that you're not perturbing while you're doing it. And all these things are probably somewhat helpful, but again, the other thing you can do is, in a language like Newspeak, you can actually run your JIT against a platform that isn't the platform that everyone else is using. You can have your own copy of a platform with its dictionaries that no one is mucking with and you keep stable and things like that. And there's a little bit of memory overhead to that, but you protect yourself from whatever is happening. So there are reasons for having real modularity in a language, but I know this isn't anything that will really solve your problems in Smalltalk in practice.
Well, Gilad, I did want to say that it's key. It's a key element of the ability to use the simulator, to have Scorch alongside the simulator as a peer to the rest of the VM, to use mirrors, because then you have to have a mirror interface so that Scorch believes it's talking to the local method dictionaries, but in fact is talking to the method dictionaries inside the simulated image. So yeah, your mirror architecture is actually key to being able to do that. So yeah, I would start off by implementing a valid set of mirror implementations, even if they wouldn't be anywhere near as elegant or complete as what you've done, to be a hack. But it has to be done. That's the only way to practically architect it.
But I think, like, can I explain? No.
Sorry.
I wanted to say, I think, like, what Gilad mentioned, I think there is a more general problem, which is like, what is the interface we provide between, like, the VM and the runtimes? And, like, being able to poke, like, the method dictionary is not very practical. It would be much better that you will, like, give intent to the VM, like, I'm trying to install a method now, or, like, modify the method. So now we have these, like, small hacks in all the runtimes, which is like in @part of method dictionary, we call the primitive flush cache, which works. But the thing is, if you want to update anything regarding this interface, it's horrible, because you need to update, like, all the different runtimes. And what is really nice, for example, in Smalltalk, or what Pocho is doing, right, is then you can change that, right? You don't have that problem, right? So if you guys together, like, are doing a joint VM effort, like, I'm wondering, like, are you going to support, like, all these different, like, images that we have now, or are you going to build a new one, or I don't know, because, like, can you redefine that interface in between, like, the Open Smalltalk VM on the different language, or, like, is it something which is there and you'll have to deal with it, right?
Well, that's a good question. Let me come back to it in one moment. So the platform idea, Gilad, is definitely present in Pocho's work, right? In Rich's work, right? You have a minimal Smalltalk kernel, and it's against that you write the JIT. So that's not the same thing as Newspeak, but it meets the same necessity, that you have to have a small and defined kernel, which is a known entity and is not subject to the programmer changing things. And Clement was hurt continually by that. So that's vital. But to come back to your point, Clement, can you remind me what your point is? I hate doing that.
I'm just wondering, like, if you're doing a joint effort together, like, are you going to keep, like, to build yet another image, or to keep everything working for all the current images with the existing interface with the VM?
So the experience is that if what you have is compelling enough, then you can force conformity. So Spur was fast enough that everybody was willing to change their image format. So if you don't bring anything interesting to the plate, you can't force conformity. Sister, if it does what it says it will give us 3 to 4x performance increase. Spur gave us like a 40 to 50%, maybe a factor of 2 increase, right? Spur gives us potentially twice as good a benefit. With that benefit, you can force conformity. Now, that doesn't answer the other question, which Gilad and you were both raising. What's the right architecture, right? Because we can do a lot better than we're doing with kind of an old Smalltalk 80 idea that you know was developed in the 80s. So there is a way to go, and the you know my kind of the only thing inside that kind of makes me feel is you want to maintain the freewheeling thing that you have. You don't want mirrors to become some obstruction. They must be an enabler. And so I'm kind of really curious, Gilad, maybe when I do come to do the simulator work, I'd be able to call on you just to like get some really solid advice on how to do it as not I'm not concerned to do it kind of right as to do it fluidly. Is to it's to make sure that there's a simple conceptual model and that effecting the changes that you want still remains natural.
Sure. The thing is, of course, there is a tension there. And I'm still not satisfied with the mirror interfaces we have, which are still evolving as in Ryan's latest work. And it's still, it's a challenge to make it as fluid as it is in Smalltalk, because you have put up a barrier there for all these reasons, and then you constantly have to walk over it, and it isn't as fluid as it should be. There's a price.
Yeah, well, we're all in that boat.
If I could give an existence proof, in the Green Book we have Loom, the large object-oriented memory, which is a virtual memory that was implemented entirely in Smalltalk. And the way they did it, they had two Smalltalks running side by side.
Yeah.
So the virtual machine code was in this tiny little image that wasn't itself a virtual memory. And then you had the user image that did have virtual memory. So the user image didn't see all the little tricks, all the little object formats. That was all hidden in the little implementation image, but they were able to program in Smalltalk, but they weren't changing stuff so that they were breaking their own code, because that was on the other side of the barrier. So there was this fence, and you were developing here. So it's very much like the simulation that Eliot is talking about, except that the two had an interpreter that kept switching back and forth from them. So they weren't one on top of each other. They were side by side. So it's been done a little bit.
Okay, guys. So sorry to interrupt again. It's time to pass to Giselle. So thank you, Clement, Eliot, for the discussion also. And okay, so Giselle, it's your turn.
Thanks. So can I share my screen? Yeah. Where is it? So here's the whole desktop. Sorry, I was trying to find the window. So where's the chat? So can you guys see this?
Yes.
Yeah, I can see it and hear you.
Okay, having a chat in the way here that I can't seem to get rid of.
It doesn't show up. It's fine. It looks like you've got it right. We just see the warm window.
Okay, So this is just going to be quick. It's just a very simple idea that I started to implement in the early 90s on a machine based on an ARM processor. And it was a very simplified version of the self virtual machine. I was writing it in ARM assembly code. And the reason why it didn't get finished was I was actually had to, every change I had to change the EEPROMs for the machine. So I pull out the EEPROMs, erase them, ultraviolet lights, program them again, and the flexing of the board eventually made the prototype stop working. So I went on to other things, and I eventually got a second prototype to work, but then it was too late. So I'm going to go through a very quick introduction to the ideas. What is PICS, the polymorphic inline cache? I think that practically everybody here knows even more than I do about this, but some of the people that might be in the streaming might not be familiar with the ideas. So this is a normal language like Fortran or BASIC. What you have is a symbol table that associates names with places in the, if you're compiling then machine code, if you're interpreting then some form of the source code. And when I compile, I don't have to keep the symbol table handy. I can generate jumps directly to the place indicated by symbol table, and I can have a binary that I really don't need to the symbol table anymore. Some languages have a block structure like Algol have a more complex symbol table, but we'll ignore that. What's interesting is if we go from this to object-oriented programming languages, essentially we're adding a dimension. So the symbol table becomes 2D, where it was 1D for imperative languages. And that's actually the bulk of the power that object-oriented languages give us is this 2D structure. And somebody looking at that might say, oh, if 2D is good, then what about 3D? And there's a lot of research in context-oriented programming, subject-oriented programming, so on. Let's not go there. Let's just look at a typical example of this 2D table here. So what's the size of this table? So I'm showing this in Eliot's development image. So this is legit compiler. So a very, very typical image. So how many columns do we have? If each column is a class, then this image has 7,111 classes. This is actually the class and the meta classes. I'm considering them separately. A column for the small integer class and a column for the small integer class, or something like that. So how many rows do we need? So we have 52,000 rows. Okay. So let's do the math. I'm going to change this a little bit. Sorry about that. And 34. So I've added some classes and methods for this presentation since I did this math. Oh yeah. So we have almost 400 million. Let's make this easier to read here. we have almost 4 million entries. 400 million entries. So if each entry has several bytes, then that's the reason why we don't normally implement our languages like this. Of course, out of all of these, almost all of these entries in this table would be empty. They would be a jump to does not understand or a call to does not understand. So of these almost 400 million, only about 7 million of them would have a non-error entry. So we can actually do the math here. And the numbers are a little bit obsolete. They're not exact, but it's not going to change too much, so I'm not going to correct it. So it's about less than 2%. So less than 2% of these entries are not empty. So this is a very wasteful way of doing things. So if I were to compress each column using a dictionary, so let's do that. So that's a traditional Smalltalk implementation, right? So I extracted a column. So this is just one of those columns, and I've eliminated all those empty spaces by implementing a dictionary. And in fact, I went one step further. Because there is a subclass-class relation, I've eliminated all of the redundant, because really what this class should have is something like this. Really bad with, and now I can't get to the button. This little window that I can't get rid of is really getting in the way here. Okay, so it would this class is supposed to have this very long dictionary which has all of its methods, but most of its methods are inherited from the superclasses. So I can eliminate copying them. So what happens if I do eliminate copying them? Then I get only 92,000. So out of the 7 million, most of them are redundant. In fact, these numbers are very, very skewed for this image because we have more than 500 methods on objects, and then everybody inherits from objects. So that these numbers, more something like little Smalltalk or other Smalltalks would probably have more reasonable ratio of the number of total methods to the number of actual methods, not inherited ones. Now, the advantage of actually copying the code from the parent is that I waste a lot of memory. I go from, like I said, from 92,000 to 7 million, but then it's fast because I look in this dictionary and it's there. If I save space, then I have to do pointer chasing. I have to look in this dictionary, it's not there. I look in the parent dictionary, it's not there. I look in the parent dictionary, it's not there. And there's a trick that we can't do in Smalltalk, but if you have some extra information from the person sending the message, like you have in Simula or C++ or those kind of languages, where you so if each, I'm showing here two different object trees, you can't share methods. You can't send the same name to the different ones. You have to say what type you're sending the message to. And then in that case, we can uniquely number, we can associate each selector with offset. That's what we call V tables. So that's why these languages can be a little bit faster than Smalltalk, but at the cost of not allowing you to have objects that live in different trees use the same high-level code. You can't do that. So then you get all those horrible class templates and stuff like that. So of course, if we instead of interpreting, like these are the symbol tables from our first slide, if we compile code, then we can actually do a simpler trick, which is here, these are compiled methods. Okay. So on the left, we have what we call an inline cache. The inline cache is actually a call to a little block of code, which I'm showing it in this magenta color or something like that. This code will test that the class of the receiver is actually what the code that follows it expects, this bluish code here. So if I call this guy and I find that it's not the same thing, then I go to the general lookup code, like if I were interpreting. And what this guy will do, it will see if I already have compiled that code. If I haven't, I will compile it now. And if I have compiled it previously, then what I'll do, I'll change. I'll change to the actual class that this code is, and that also has it checks to see if it's correct, and then executes it directly. So, except for this little purple thing which checks the class, this is almost like a normal subroutine call. As long as every time you call, the class is the same as the previous one. If you have this situation where it was one class before and now it's a different class, and if you call it again, it switches back to this. If it keeps switching back and forth, then that's going to be very slow, and you don't want to do that. So what could I have done instead of switching, having the lookup, switch the pointer of the caller? I could have changed this to actually call a little code fragment that we're going to call the polymorphic inline cache. And what this will do is it'll do the check. Oh, this is very awkward. Now, since the check is already done, I can jump directly to this code. I don't have to check twice. So there it is, right? And so that's unchanged, but now I can do the second test, jump directly to its code, and so on. So now this is actually not very inline, but that we kept the name, we extended the inline cache, so it's the polymorphic inline cache to pick. And this has a very interesting advantage. If I keep this pick updated, after I execute a while, I know all possible types, or not all possible types, all the types that I've actually seen in practice during the execution of this call thing here. So that saves a lot of time. If I want to recompile these set of methods with a better compiler, I can use this type information to generate much better code. But if I'm not going to recompile it, if I have a very simple compiler, which is the proposal here, which compiles just once, then I'm going to have a simpler alternative to the pick, which unfortunately does not accumulate type information. So, so far I've been sort of looking at that table in terms of rows, but now I'm going to do it in terms of columns. So what happens is I'm going to translate the send message to a call. And again, it calls into a little piece of code. In this little piece of code, the first thing it does is actually load the class. Now, in the inline cache, in the polymorphic inline cache, normally this code was actually right before the call. But for some VMs, it can be a bit complicated. You have to test if it's a small integer or not. Then you have to, the older squeak, you had to see if it was a compact class or not. So there are all kinds of complications. So to save space, I'm putting the load class right after the call rather than before, as normally done. Then you check the class. And if it's the correct class, you just fall through and execute the code. If the check class fails, then I load into a register the fact that I started my lookup with this particular method. And then what it will do is it will jump. It will jump to this code here for a different class. So after you finish loading it, they'll jump here. And this will check to see if it matches the first. If it matches the first, then that means that we've gone all the way around. This is going to be a circular list of all compiled methods that are associated with a given selector. So this is a row in our table. And if it doesn't match, if we've already gone all the way around, then that means that we might have to compile. It's the equivalent. So here it goes to lookup. Now, if we haven't tested all classes yet, then we check that the class is correct. And if it doesn't match, if it doesn't match, we call the next one. Really having a hard time here. And start the process again. But if it does match, then it will silly now. If it does match, then you just jump to the, sorry. Actually, this is wrong. You actually have to jump to a code called patch, which then calls the method. So what patch does, it will change this pointer from this pointer here, from this method to the equivalent header of this method here, and then it'll call this. And here is the same thing. If it doesn't find the thing, it calls a lookup, and then there's also one equivalent for this. So you basically form a circular list. In this case, there would be these 3 entries in the circular list. So if you call this, the class check didn't work out, so you load it first. You check the first, it's not the first. Is it the class? No. So you check first, no, class, no, and then you go back to this beginning. Then you check first, yes, there were 3 entries, and I've looked at all 3 entries, and then so you go to lookup. So basically, you have you have these 3 sources of overhead. You have this little load thing check class, this load first, and then these 2 little blocks. So each of these are like 2 or 3 instructions long, and you have to have one of these for each compiled method. And every time you call lookup, you're going to change this list. And of course, if these methods live in a cache, you might have to make room in the cache, so throw some of these guys away. So you have to patch the thing again. But the point is that this arrow here acts as an inline cache, in that it either points here, or it points to the second one, or it points to the third one. So it can quickly switch between them. But in the inline cache, you had the full overhead of lookup every time you missed. And well, here you have 2 levels. The first level is just going around this circular list as fast as you can. And then if that fails, then you go to the lookup, and so it's as costly as the inline cache. So this sits between the polymorphic inline cache. It's not as good as a polymorphic inline cache, but it is better than the simple inline cache. So it's an intermediate level. I find this interesting for very, very simple VMs that still compile. This doesn't work with an interpreter. So that was it. Hope it was possible to understand here.
Yeah, I want your chops. I like being able to use Squeak for these kind of interactive presentations. That was very nice. I think that they're very close in idea to the Smalltalk V setup, where they implemented their inline cache by having a 1-element class in front of the method. So there's a direct call, the method loads the class of the receiver and then compares it against the class immediately in front. And if that doesn't match, what they do is do a lookup, and just as your analysis showed, most methods are inherited. Most of the time when you relink, you'll link to the same method. Most of the time picks are not fan outs. They're actual fan back in. They have, you know, this class uses the same method. This class, you know, 4 different classes use the same method or whatever. So they would extend the method, this one element class thing into a vector, right? And that's right, isn't it, Pocho? That's basically, and so your scheme, it seems to me, is perfect for generating code for the metacircular JIT, right? Because we don't have to compute any picks. It's kind of you know, we have a closed world assumption when we translate that, and since the JIT, as we've seen from the pause times, when we looked at COG, we were only seeing the cost of reclaiming the code zone. Generating new code is so cheap that it's difficult to measure, right? It's kind of
now, a difference between what I showed and what you were talking about is that a single source bytecode might get translated to different machine code for different things. So that's customization. You probably want that if you're going to have any kind of inlining. But so for some methods it's worth it. For other methods you could share the machine code. So you still have one little header for each class that inherits the source method, but they could all point to the same machine code if you're not going to customize. And unless you have messages to self that you can inline easily, then probably for a simple compiler, customization is not going to be worth it. So that would be my criteria, depending on the size of the method and depending if it has messages to self or not. I'd customize it or not, or have the various elements in the linked list point all to the same machine code, so save memory, and probably have a flag there, say customize or not.
This remembers me very well of the original implementation that we had. Maybe Javi or Ronnie will also remember, because in the original work of V, we used to generate a closure of code for a DLL. For a garbage collector into a DLL. So there you had all the methods that were going to be executed, for example, by the garbage collector. And then you could, ahead of time, generate the list of the possible implementers for a given selector, and then just call a loop that checked each of them, and either, execute them, or if you got into the end, that was probably an error in the closure because you were sending a message that was not understood. So I think that it wasn't circular. I guess that adding the circularity lets you make it faster because you can start by the latest closer receiver, right? If you start always from the end, you have to go through all the list. But if you make it circular, you can start from the last you found. So that's nice.
And each call set can go in from its own point, right? So you can have multiple indexes into the ring. Right?
And well, one thing that I wanted to say also is that I think that this is also possible to do in the BDMR because of the way that sends are implemented with objects. You just call some code, and then that code could be anything. It could be a monomorphic inline cache, or it could be this kind of inverse lookup, or whatever you want to call it. So you just have to adjust the assembly that you generate, and which is usually a small stub, and then you have a cache object or a cache slot in the send side that allows you to put whatever you want. So probably that's going to work. We can try it on the hackathon. Yeah, it's very interesting.
Yeah, one point why I really like Giselle's scheme is that, well, I have not actually tried it, but it does look like it allows for much faster path to actually starting to play with this scheme, especially when you fundamentally change the meta-object protocol. For example, if you wanna switch between squeaks or traditional Smalltalk 80's relationship between instances and classes and the ones that B uses, when you have picks, it looks like you're going to spend a lot of time before you have something on your hands which you can actually play with. And this is, this is simpler. So for what I am trying to do, which is, trying to experiment with various meta-object protocols that do not resemble the one in Smalltalk 80, this seems like a huge win in productivity when you can just try this meta-object layout or this meta-object layout or this other one, and yeah. To actually try this at the hackathon tomorrow, like at the hands-on hacking tomorrow, does seem like a perfect idea to me.
Do we have other questions around? Well, if we don't have any more questions, that was okay.
Pocho, sorry,
No.
there is a
Can we have a
question.
quick break for a cup of tea?
Chat. 2 questions on the chat.
Okay.
That's weird. I'm not seeing, like, in my chat window, I'm not seeing.
So one of the questions is actually for Eliot, and I read it during his talk, so it has been there. Yeah, it's a bit old, but
Good to hear your voice, Javier. Well,
yeah, yeah, yes. Hello.
hi.
So yeah, well, I had this question about object tables, right? So yeah, instead of having direct pointer, right, to have a table with all the objects, right? And then the object, I think Gemstone do this, but I am not sure. And every object has a point. Yeah. Yeah, you know that. So my question is whether you have tried.
Yeah, I mean, I grew up with that style of VM, and the VisualWorks VM has it doesn't have an object table until you get to old space. So in new space, a VisualWorks object header has 3 fields. It's got a bits field for the garbage collector. It's got the class pointer, and then it's got the pointer to the body. And in new space, the pointer always points to the next word, and the body is next. Yeah. And in new space, in old space, they get separated. So then you can do a become by just swapping pointers. So it's very fast. The problem is the constant indirection. So you pay for that indirection on every instance variable fetch. You pay the space overhead on every allocation, right? Yeah. And when it became ridiculous was when I implemented the 64-bit system for VisualWorks. So there, I couldn't.
Yeah, I can see that.
Right, I couldn't have 3 64-bit words. So there, I got rid of the class and used class indices. So there's like a 22-bit field for class index and a 22-bit field for the identity hash. And the way that you make that work is that a class's identity hash is its index in the class table. So whenever you want to instantiate a class, you have to make sure it has an identity hash, and you give it a unique identity hash. And then there's a sparse table that matches class identity hashes to class objects. So if we want to instantiate a class, all we do is we copy its identity hash into the class field of the instance. So now the instance points to that class indirectly through the table. But it means that in inline caches, you only deal with the class index. And it also means that things like message, array, compiled method, string, etc., they have a known class index. So now the header is a constant. We don't have to go and find out where the class is at any one time. We can just instantiate an array immediately, right? We know what its header looks like. So class indices save you a huge amount of space when you go for 64 bits, and you get a lot of efficiency. But I still had the 64-bit indirection pointer, which was ridiculous. And I remember at a Smalltalk Solutions, somebody saying, you should make that 32 bits. And you know, that's right, but it was a big change to the VisualWorks code base. It was easier to keep that ridiculous 64-bit indirection. So if you look at the HPS 64-bit implementation, there's a 64-bit word with the class and the garbage collector bits, and then there's a 64-bit word to point to the body. So it becomes incredibly fast, but you're paying for that a huge amount of space. You have twice the object table overhead, right? And on every instance variable access, there are short sequences where you can cache the base address, but essentially you're paying for it all the time, and so.
So let me say, I've been thinking about this, and I know that you know that, right? So it was a bit redundant, but two things. I am not working on VM, so I don't have this fresh, right? But what I understand that you pay the indirect cost, but I see this more like an amortized cost for the other things that it give you, which at least I see two. One is that you can have a garbage collector running all the time, right, in a separate thread, which is great. And it's amazing. Actually, that is amazing, right? So if you want to have 50 frames per second, you will not stop. So that's great. And the second thing is that I don't know how B is working now, but 10 years ago, every time you do a full garbage collect, you have to remove the code cache, right? Because in the code, you have pointer to well, this is how B was working. Yes. So we had pointer to objects, right? Yeah. Direct pointer. And that's the thing. Okay, you just actually describe one of the things, right?
Thanks.
Yeah, what?
Thanks to Yang, we don't have pointers anymore in native code. Yeah.
Okay. Okay, that's great.
I think direct pointers actually pay for themselves, and I have direct pointers in the code, and I really appreciate the speed you get. I mean, on ARM, you're always using PC relative addressing to get to the thing, but yeah, we have all of the metadata in the code to allow the garbage collector to transfer. It used to be the absurd thing in HPS that at the end of the incremental collector, where you'd spent all of this time doing these tiny little amounts of scan mark, you would then throw away the whole code zone, and and you would notice this huge slowdown. So I don't like to pay for the
wait. Just for my own benefit here, of my own understanding. I'm sorry if I am interrupting. My understanding was B never had a code zone, right? Because the code is embedded in the objects. Is that right, Pocho?
Well, previously what we had was an object that RAID 5 native code. One of its slots was the byte array that represents the code. The byte array could be anywhere, so there wasn't an actual native code zone. And the other object was an array that had the references or the offsets to the references to objects. So when you were garbage collecting, you will find these native code objects and use them to trace the references in native code. That was the way it worked before we removed native object pointers from native code.
Yeah, but at some point, actually, when you garbage collected, you put to 0 the pointer to the native code array, right? You nil it.
Yeah, when we were garbage collecting, we had to update all the references.
Yeah, but before updating, I mean, in a previous version, we were just dropping the code.
Of course, yeah.
I'd just like to mention that there is a Squeak VM called the Roar VM for multiple processors, and it uses object tables. So
okay.
You can,
how is it called?
Roar VM. I'll type it in the chat.
Oh, that's the Stefan Mar thing?
Yeah, it was done by David Unger.
Oh, yes. Sorry. Yes. Now I remember. Yes, you're right.
Okay, thank you.
So Javier, the thing, are you familiar with Spur?
We what, saying?
Spur, S-P-U-R.
Oh no, I am not actually. But well, yeah, I saw you.
I'll point it to you. But basically, what you do is you keep direct pointers, right?
Yeah.
But you make sure that every object has space for at least one pointer. So a zero-sized array is an object header plus an empty field, right? So the minimum object size is always 2 words. So with that, you can turn any object into a forwarding pointer. And so what you do if you want to forward is you then set the first field to point to where you want it to point to, and you change the header. So you destroy the class. So now when you try and access this object, it always fails, right? And so because you're always doing lookups, right, you get this implicit read barrier from message send, right? So then one of the interesting things that you want to do is you want to avoid that read barrier when you access an instance variable. So because the stack zone is limited in size, it's very quick to scan that. So you always scan the stack zone and follow all forwarding pointers in the stack zone. So there's never a forwarding pointer to the receiver. So fetching an instance variable, you never have a check, right? Mm-hmm. And you have a check when you send messages, and you have a check when you do primitives, but you check anyway because you're doing the message lookup check and you're checking for arguments. The only time you don't have a check is for a supersend. So supersends, they're infrequent, but you have to add an explicit check because a supersend is statically bound, right? So then the next thing is that, okay, in Smalltalk, a global variable is an association. So in the code, there would be an association, right? A pointer to the association, and you have to fetch the value of the association to find the class. So, array, a reference to an array in the code is the association for array in Smalltalk. So the first field points to the symbol array, and the second field points to the array object. So the code refers to that pair, right? And you fetch the value to get array. So now you have to do an explicit check because you could have become that forwarding pointer, and you could have become array, but you don't care about this forwarding pointer. If you send a message to this forwarding pointer, that will hit the message send trap. But you do have to check is the pointer to the global variable forwarded. So in our first version that Clément and I did, that was what you had to do. But then we realized that we have a list at the end of the code zone for the objects that contain references to new objects, because those get visited by the scavenger, right? And they're a tiny subset because most methods are referring to old objects. So we just extended that list to refer to all of the methods that contain references to globals. And those are very, very small too. So we've got this small list at the end, which is the objects that need to be visited by the scavenger, the native methods that need to be visited by the scavenger, and the native methods that contain a global variable. And so after a become, we traverse that list and make sure that all of the pointers to global variables are not forwarded either. And then we don't have to check, right? So the game that we've played within Spur is that instead of paying for the indirection on every access and having the simplicity and the speed that you get with the space overhead, is that we use a lot more complexity, and we use the caches in the VM as ways of restricting the following of the pointers, so that we don't scan the entire heap. So we don't scan gigabytes, but we scan only a few 100K bytes, and eliminate most of the explicit read checks that you would need.
That's very interesting. Well, thank you actually for explaining this. But there is one more thing that I would like to say, which is, thank you for all the things that you say at the beginning about B, right? All the work that we did with Hera, with Pocho, and Leandro, Valeria, all the people working on this. There is something very important that you say, which is that you would like to submit something to PLDI. I strongly believe that most of the work that is happening here in this community is staying here, and that's a pity. It would be great if people outside of the Smalltalk community know all the things that you do, right? And it's gonna be hard, right? To get a paper into PLDI, it's a bit hard. But yeah, I think you totally do that. That would be great for the community. So,
well,
yeah.
there's a story behind that, which I think is really interesting, and Clement will correct me, but you know, we were publishing a little bit, and most of it was kind of workshops and stuff. But then Clement left INRIA Lille and went to Brussels to work with Elisa Gonzalez-Boix, who, you know, is a publication monster. First of all, she's lovely, right? She's really nice to work with. And second of all, she really knows about publishing. And she supported Clement and I in writing, and Clement in writing some good quality papers on Spur. And without her help, and without help from Richard, what's his name, the GC Handbook guy, we wouldn't have written that.
Richard Jones.
Yes. And then what happened is Eliza made it possible for Clement and myself and Dan to collaborate on the paper that describes 20 years of the simulator, right? So starting off from 1994, and referring a bit, because, you know, Dan first did his first simulation when he moved from Smalltalk 74 to Smalltalk 76, or maybe it was Smalltalk 72 to, yeah, I think it was 74 to 76. So he's been doing this for a long time, right? And it's really his idea. And so it was very natural for the Squeak team to do it in 94 to 95. And then I got to, I was introduced to it when working for Gilad for the first time, and then with Quack. So what's happened is since 2008, when I started, you know, we took that interpreter simulation environment and turned it into a full JIT simulation environment, and then we implemented Spur, this new memory management thing, and we implemented Clement did the bulk of the work on Sister. So we got to write up that 20-year experience as an SP&E paper, and it's now a journal paper. And the last time I checked, I had 984 reads on my ResearchGate page, which is like 200 times greater, 100 times greater than any other paper I've done there. And so, you know, this thing of actually being able to publish really good quality work to the premier virtual machine workshops and to journals really is worthwhile, and it's something that we must do. You know, we've got fantastic attention, and I'd be curious to check. I'm going to check with you, Jan, whether Clément and I, our work with Spur was any kind of inspiration into that work that's in J9, because we've, especially Clément was did a full literature review as we wrote the Spur papers. So yeah, we should.
Great. But this is going to help the whole community. This community, these people, is going to help a lot if you get into PLD, I say, or Popular, I don't know. But yeah. Okay, well, thanks.
We should try to get back the conferences that are about object-oriented programming, because usually they are not even about object-oriented programming anymore. When you see UPSLA, ECUB.
Hush my mouth. I mean, this is like super important. So for me, being in 3D ICC, using Squeak to build Croquet to build a 3D communications thing is fantastic. It's a real environment in which to validate ideas, validate the technology, and so to try and produce something that is stands against Zoom. I mean that's what we're trying to do. I think that's very important, but it comes back to the ideas that Joseph Pelrein introduced me to in 2017 that I started talking about 2018 in FAST, which is this idea of economic viability for an open source community. So if an open source community does not construct itself carefully enough, the open source license is not an open source license, it's an open available license. It's anybody can come in and use what you have, and you get no economic benefit. And the New Commons movement, Mikkel Bauwens is one of the leading intellectuals there, is about any community really learning from older structures like the Middle Ages Guild or water sharing on Bali, etc., in terms of and a number of modern communities, in terms of making sure that the open source community is a capsule which retains ownership of its IP and only grants access to the IP to commercial interests if they pay. And so the challenge is for the open source community to collect the funds, retain ownership, and spread the money back out to enrich the community. And I don't want to go on too long, but I would say that this is actually cogent thought. There's some kind of structure to it. That if you look at the communities that have done this, and in Bowen's example, there were an agricultural collective where people are trying to allow farmers to break out of the control of tractor manufacturers over, tractor upgrades and electronic controls and stuff, break out of the John Deere restriction, and have farmers and agronomists and mechanics and computer people be able to communicate to what is called Farm Hack and runs on like 4 different continents. And then a group of journalists in New Zealand who, after the 2008 crash, found that their editors wouldn't allow them to write about the true financial causes of the crash, and they set up their own website so that they could self-publish. And then they ended up selling the website authorship software and also the decision-making software that they developed for organizing this self-publishing organization. And then there's another couple of examples that he gives. In all of these examples, what you see is 3 institutions. There's the community and its internal decision-making. There's the intellectual property and the license to retain control of that. And then there's a kind of a marketing arm or a sales arm, which is the interface, controls access to the IP, collects money. And then there's various magic by which the money that comes in from the outside goes into the community, because it's not just programmers. You could have video makers, documenters, testers. If this economic viability is done right, it allows the community then to use its funds so that it's not just what we do, which is programming, and we don't have time to document. Right? It then allows us to actually build something which is not corporate, but functions as efficiently as a corporation. And so I think it's really, really important that as a community we start to investigate this, and that this is as an important an activity to put alongside what we're doing with the VM, right? Because if we get this right, it means that we really can grow not just along our axis, which is implementation and design, but all of the other axes, tests, production, talking with customers, marketing, education. One of the beautiful things, I was very lucky with Doru Gerber to be to get a contract in 2016 with Lam Research, the silicon people, to investigate using Faro to break them out of Rudolph's software. Wasn't successful because of the lawyers, but in our relationship with Lam, we found out that they have a very, very interesting planning structure. So the situation with silicon design is that there's lots and lots of interesting surface physics, and each discipline is incredibly well developed, right? And there's all sorts of processes. Most of the chips that we use in our phone go through 200 distinct steps. And there are processing steps which might be like deposition of some gas or whatever, but there are other processing steps which are like irradiating the wafer with specific shaped waveforms. So the amount of physics is extraordinary, and then there's the robotics, etc. So what they decided that they needed as a planning council were 20 T people. And a T person is somebody who has great depth in one area, but enough breadth that they can bridge to the next T. And so you cover the field. And so they had 20 scientists who were chosen for their deep expertise in some area and their ability to span, so that they could cover the entire of surface physics, because they aimed to be 18 months away from publication of research to deployment in product. And so to keep that pipeline going, they had to have the breadth. They also had to have the agile practices that I talked about earlier with PhD students, where PhD students would be guided. Okay, you started on this topic. That topic is actually dead now. We want you to move over to this, or whatever, right? So that the PhDs, when they publish, produce something that the company could use. Well, a 20-person T structure was supported by 4 paper writers, whose job it is to translate the understanding that the T scientists have of the field into papers and into internal communications for the rest of the engineering organization, to actually allow the collection of this knowledge to get through to the application in the development of some new wafer, right? And that kind of like meta organization is absolutely the kind of thing that we need in order to be effective communicators, effective engineers, not so much effective engineers, but effective communicators and effective welcomers of new talent. And the only way that we can do that is if we recast the economics of the open source. And it's not all done in this awful amateur way where we can be exploited by whoever has the money. We have to encapsulate ourselves, become more radical. rant over.
Yeah, I don't know. Yeah, they know how to do that. yes, I agree with you.
I'll send you some papers, Javier, because
Okay.
people are doing it already. What's really funny about this, right, is that the people who are not doing it are the open source community people who you'd think were like most able, right? They know the technology. They started open source first, but in fact, it's communities outside, like these journalists or the farmers, right, who are actually bending the open source idea to some better.
Eliot, the issues you are raising are extremely interesting, are relevant. Maybe they are beyond the time we have here, but nevertheless, the first things that what you say makes me think is that I agree with your intention, and I think it would be a good thing to do. But what I'm afraid is that it could limit the adoption of our work by other open source projects. Okay, and if you have a chain of dependence, open source project A does stuff and protects it in some way that works, like you say, I don't know how, and then open source project B tries to do the same based on project A, then what are the limitations or the obligations for project B, and how should project B distribute the money it could collect in a fair way so it also reach project A? And maybe project A is no longer active or is some years old. I mean, there are many things this could go, and it should work smoothly in a variety of scenarios. And I guess this could be one of the reasons why many open source projects would not jump to this attitude. You say that it's surprising that the open source projects are the ones not doing it, and I guess some of the reasons may be my concerns. I'm not saying it shouldn't be done at all. I think it would be great to be able to brainstorm and discuss these issues in more depth.
Yeah, I want to say that your expression there is extremely important. The two things that come to mind in response to it, one of the things that we've done in 3D ICC this past year is license the X264 video compression library. And back in 2008, we didn't, because they had very difficult terms. And we went to a private company and paid like $24,000 a year for the main concept codecs, and they were ridiculously expensive. And what we've come back to and found this year is that the X264 consortium have changed their rules. So their rules are now, it's free unless you have 1 million customers. When you have 1 million customers, we're interested in you. So this is the Netflix world, right? Where a company like Netflix has 1 billion customers, right? And when that happens, everything changes. The open source community, you can allow them to adopt. You just have to say, okay, at one hop, the guy who uses your stuff is the guy who has to pay, right? And if you're in this world where you're talking about truly global software, being able to say, well, if you have 100,000 customers, yeah, it's fine. Don't worry about it. That's the grease that you need.
Okay, thanks a lot.
So, Eliot, I think that one way to consider your idea and not just throw the idea here and everybody forget about it because it's important, I think is to start a way to educate ourselves, at least the ones that are interested in this. And so if you have something to read or something to watch or whatever link you can provide, please send it to me or to whoever you want in the community. And maybe we can form a group that starts educating themselves about this, and then have an informed discussion on options, etc., trying to address and prevent any side effects as the ones that Juan just mentioned, because I think all of these can be overcome in a very natural way, but provided we have a good understanding on how to do it.
Yeah, thank you. I'll definitely do that. I'll get you some not too much. I mean, there are books available now. You know, there's like an explosion in the New Commons movement, but I'll try and get like 3 or 4 concise pieces to you by the end of next week. Please nag me if I don't do anything. I'll try and get it done over the weekend, but I will get you the pieces.
Excellent.
I just mentioned that Brad Cox, one of the 2 inventors of Objective-C, actually spent most of the 90s working in this area. He didn't work on open source, but he wanted to charge for the use of the software rather than for the copying of the software. And so he sort of went to a closed source thing so that people couldn't hack it, so that they wouldn't have to pay their bills. But the advantage is that the money flows from the end users to the various the tree of developers, rather than the money going to the first guy and then he has to license some library or something like that. So that's complicated, because if somebody charges you like $20,000, it might be too little or it might be too much, depending on how much use your application gets. So by having the money flow from the end user directly, a little bit to you and a little bit to the author of the library that you've used, by accounting every little piece separately. And another advantage from the Smalltalk viewpoint is that you could focus on objects rather than pieces of code. So if Tim draws a nice little logo, if that logo gets used a lot, he could get a little money of that, even though there's not a single line of code associated with it. So if we had some scheme like that associated with objects, then anybody could contribute a wave file to have a nice sound inside Squeak or something like that, and they get a little bit money from that. It wouldn't be limited to the coders.
I've just posted to the chat the paper that that Joseph Pelrein gave me in 2017. This is an excellent starting point. Please, if you're interested in this, read that paper. That paper is excellent.
Yeah,
and then you can follow.
I'm looking at it.
Yeah, you can follow afterwards, and I'll collect some stuff that follows up. And for the old lefties, you know, this like the current pandemic is you know, this is a thick book, but it's called The Great Awakening: New Modes of Life Amidst Capitalist Ruins. So there's a real global movement here in terms of being able to get some autonomy going.
Can you show that book again, please?
Yeah. Oops. I could type it into the chat. Why don't I type it into the chat instead of everybody typing it? It's a whole series of very, very broad range of perspectives on the issue. It's not just one group.
Guys, I don't want to spoil the party here. As always, Smalltalk leads to meta thinking, and meta thinking spreads to all other things in the world, not just programming. So this is just one more case of this kind of thing. We are running out of time, so I think that regarding these conversations, which are more of let's say social, philosophical, they have many corners. We can continue talking about them tomorrow during the hackathon. And what we could do right now, I don't know if that was the plan, is to try stuff so that we get prepared for tomorrow. It's not that we are going to really do something with what we are going to prepare today, but tomorrow we should have everything ready by the time we start. So it's better to try to configure things today.
I'd like to propose that we don't spend tomorrow with a continuation of the conversation that we've just started now. I think Leandro is right that we need to start off a group, and that this is an important activity in its own right, and it buttresses it. It's alongside. It strengthens what we're going to do tomorrow. But we've come together to do the VM thing. I was overcome by emotion earlier on. I'm so excited, and I'm so grateful that everybody is here. Thank you so much for your attendance. It's a really lovely, exciting time. And so, yeah, let's hack tomorrow. Let's have fun and dig in and find out and do what we came to do. But we'll keep this background, this meta thinking, because it imbues everything that we do. It's natural for us. What's interesting is kind of it's fractal. We're applying the same meta idea, right, to economic organization and the organization of our community as we are to the VM. It's beautiful the reuse of these kind of meta ideas. That's very cool. And there's something kind of it's like the life force manifesting itself, right? This pattern. You can apply, this generative pattern here, right, and there, right. So that's kind of super cool. So I'd like to propose that we hack tomorrow, and that this discussion becomes its own activity. That's really important.
Okay, then. Well, so I'm not sure. I guess that maybe Jan can tell us how to start, or I will, because for Powerlang, for the VA Bootstrap, it's just cloning some repos. For Jan things, we are going to need some more code. And also one last thing that I wanted to do regarding the previous meta thinking, it's a small apology, because today we have 6 speakers, right? We are all white male speakers, mostly the same for the audience, and maybe it seems normal, or it used to seem normal but it's not natural. And I think that this is something that we should strive to change. So I think that this afternoon went very well, and that there will be more hackathons or virtual conferences or whatever, and I would like in that case to have more a more gender equal speakers, if possible, or try to do that. So, well, with that said, okay, so what do we do next?
But you just said we shouldn't spend time on meta issues
I know.
right now.
I just wanted, because I had that already written and I forgot to mention it before, so I wanted to say it before we finished. But yeah, just let's get on hacking. So, well, I can share my screen, or you, Jan, can share your screen, or Boris, I don't know if you're there. Whoever wants,
Pocho, sorry to interrupt you, but
I'm trying to get back. I'm trying to get back this camera that just crashed for. Maybe this
Sorry, Juan. What
oh,
do you?
Sorry to interrupt, but before you start with this, please start from before. From what platform do you want us to use? Okay, not just what repo to clone, but should I clone it in a Windows, Mac, or Linux machine? With
I think it's time for Jan to talk.
It's time for Jan. Yes.
Okay. For conducting this, or participating on at the very least on my hacking, or what I propose that we can try, I created a virtual image with a Linux for VirtualBox. So there are a few people who tried. Leandro made it working. So the idea is that I will provide you a full operating system image with the Linux, which is kind of live with the persistence. So essentially all you need is just to run the VirtualBox, run the VM in it, and it will drop you into the full GUI environment with the terminal. It has already scripts to fetch B. It has already the GDB I wanted to use installed, and all sort of things. So for very least for my demo, and I believe for Pocho's, this is all set. I guess this is the same for Boris. So this should
mine is the real problem is people who don't have Linux, because and your ISO solves that. So the only other thing that you need is you just in the workspace you just go metacello new the URL GitHub blah 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 load, and that's it.
Okay, so you will get the image with a Linux and with a bunch of possibly useful stuff and scripts. Now, I was a bit nervous and stressed, preparing the talk and everything. So, as of right now, I don't have that very image online, so you cannot download it right now. It will take some time to upload it, but certainly tomorrow, I don't know, 3 hours before the hackathon, which sadly for Eliot would be like 5 a.m. Sorry for that. But before the hackathon, I will have it on a Dropbox, and I can share in the mailing list. I can share the link, and also I can share it on a Buenos Aires Slack for those who are not on the mailing list. And once you get the VM running, you are all set, pretty much.
Do you think there could be any issue by installing VirtualBox alongside VMware that I'm already using?
No issues. I am running VirtualBox alongside VMware, and I have no issues.
Thank you.
I have two machines with that kind of install on Linux and on OS X, and they both work fine.
And you might even be able to just run that virtual machine. That virtual machine made for VirtualBox might just run on VMware without many troubles.
Okay, I will try that.
Well, I made a .vdi, which is the VirtualBox native format, because when we tried with Leandro, I gave initially Leandro the QCOV2, but it didn't work for some reason. But I can probably make you VMDK and put it somewhere, probably somewhere else, because I have only limited Dropbox capacity. But I can try with the VMDK. But you should be fine with the VDI, really, and installing it alongside shouldn't be an issue. But again, I didn't try. I use a QEMU and KVM on Linux. So,
okay, thank you.
Okay, guys. So I think it's we are done, right? I just wanted to thank all of you. I had a great afternoon. The talks were great, and I feel very, very lucky to be part of this community. So thank you. And see you tomorrow.
Thank you.
Thank you, Pocho.
Tomorrow, guys.
Hola, Valeria.
Yes, thank you.
And also, I want to thank all the B team. As Javier said, there were many working. Valeria, Leandro, they are here. Guillermo was here until some minutes ago, and many more in the office. Carlos, everyone. So, thank to all the B team.
Thank you.
There is Javi.
Thank you.
Goodbye.
Thanks. See you tomorrow.
Bye.
Bye.
See you.
Bye.